What if everything we see, touch, and experience, the screen you're watching right now, the air you're breathing, even the thoughts forming in your mind, isn't actually made of solid stuff, but is instead built from something far more mysterious and fundamental? What if the true substance of reality isn't matter or energy, but something as simple and yet as profound as distance itself? This isn't a thought experiment pulled from science fiction. It's a powerful idea rising from the edges of modern physics, one that challenges the very foundations of what we believe about existence. From ancient philosophy to the most advanced quantum theories, the concept that reality might be woven from spatial relationships invites us to rethink everything we thought we knew about the universe and our place within it. We often imagine the world as a collection of objects, atoms, stars, people, and planets, all interacting in a vast, empty space. But what if that space isn't empty at all? What if it's not just a backdrop, but the main character in the story of reality? In this journey, we'll travel across millennia of human thought and scientific discovery, exploring how some of the greatest minds in history, from the philosophers of ancient Greece to visionaries like Einstein and beyond, have quietly pointed toward a breathtaking possibility. We'll uncover how relativity warps the fabric of spacetime, how quantum mechanics suggests a foamy, turbulent structure beneath the calm surface of nothingness, and how theories like string theory and loop quantum gravity propose that distance itself may be the ultimate building block of everything. By the end of this exploration, you may never look at the world or the spaces between things the same way again. We'll venture into black holes where distance loses all meaning, examine how the expansion of the universe creates new distances every moment, and even question whether time itself could be a manifestation of spatial relationships. This is more than a scientific inquiry. It's an invitation to expand your imagination, to see the hidden architecture of reality, and to reconnect with one of humanity's oldest and most profound questions: what is the true nature of existence? So settle in, open your mind, and join me as we dive deep into the mystery of why everything, absolutely everything, might be built from nothing but distance. Centuries before telescopes or particle accelerators, the human mind was already wrestling with the deepest mysteries of space and reality. In ancient Greece, around the 5th century BCE, a philosopher named Zeno of Elea devised a series of paradoxes that continue to baffle and inspire thinkers to this day. His most famous, the paradox of Achilles and the tortoise, seems to show that motion itself might be an illusion. If the swift warrior Achilles gives a tortoise a head start in a race, Zeno argued, he can never actually catch up. To reach the tortoise, Achilles must first cover half the distance to it, then half of the remaining distance, and then half of the next remainder, and so on, creating an infinite number of smaller and smaller distances he must cross. This infinite division suggests he never truly arrives. While we know from experience that motion is real, Zeno's paradox brilliantly highlights a profound question. Is reality fundamentally about the objects moving, or about the divisible space between them? His puzzles forced a confrontation with the idea that space and distance might not be passive stages but active, puzzling participants in the drama of existence. Around the same time, other Greek thinkers were engaged in a fierce debate about the very existence of nothingness. The concept of the void, completely empty space, was radical and controversial. Parmenides, Zeno's teacher, argued that the void was a logical impossibility. He famously stated that what is, and what is not, implying that nothingness cannot exist. To speak of empty space, he thought, was to speak of non-existence, which is a contradiction. But then came the atomists like Democritus and Leucippus, who daringly proposed the opposite. They imagined a universe consisting of only two things: tiny, indivisible particles called atoms, and the infinite void through which they move. For them, the void was not nothing. It was a necessary reality that allowed for motion and change. Without this empty space, atoms would have no room to swirl, collide, and combine to form the complex world we see. This was a monumental step. It proposed that the relationships between things, the empty distances that separate them, are just as fundamental as the things themselves. The void was no longer a mere absence, it was a generative field of possibility. This fascination with the power of emptiness was not confined to the West. In ancient China, Taoist philosophy developed a rich understanding of the dynamic interplay between void and form. The Tao Te Ching, attributed to the sage Lao Tzu, opens with a poetic meditation on this very relationship. It tells us that while we mold clay into a pot, it is the empty space inside that gives the vessel its usefulness. We carve out doors and windows for a room, but it is the vacant space within that makes it livable. Therefore, it concludes, we benefit from what is there but find use in what is not there. This isn't just a clever metaphor for practicality, it's a deep metaphysical principle. The void in Taoism is not a sterile emptiness but a teeming potentiality, the womb from which all forms emerge and to which they return. It is the unnameable Tao itself, the way of the universe which acts without acting, creates without being created, and exists as the ultimate background reality from which everything tangible arises. These ancient inquiries, separated by vast continents but united by a shared human curiosity, laid a crucial foundation. They established that questioning the nature of space and distance is not a modern eccentricity but a perennial pursuit. The Greek atomists gave us a vision of reality built from discrete particles and the void that defines their relationships. The Taoists offered a view where form and emptiness are two sides of a single coin, each giving meaning and function to the other. And Zeno, with his frustratingly clever paradoxes, forced us to admit that our everyday understanding of motion and space might be deeply flawed, hinting that at its heart, reality could be more about connection and separation than about solid, independent objects. This historical context reminds us that the journey to understand the universe as a network of relationships built from the fabric of distance itself began not in a high-tech laboratory, but in the quiet contemplation of philosophers gazing at the stars and pondering the nature of the empty spaces between them. Yet for all its philosophical elegance, the ancient view of space as a passive void or a generative emptiness lacked something crucial: a precise mathematical framework. That framework would arrive centuries later, thanks to a mind that saw the universe not through poetry or paradox, but through the unflinching lens of mathematics and measurement. Isaac Newton, working in the late 1600s, needed a stage upon which his laws of motion and universal gravitation could perform, and so he proposed a radical and enduring concept: absolute space. Imagine a vast, invisible, and utterly immovable container, an infinite box that exists on its own, completely independent of anything placed inside it. This was Newton's absolute space. It was the fixed, unchanging background against which all motion could be definitively measured. For Newton, if you took all the stars, planets, and atoms out of the universe, this absolute space would still remain silent and eternal. It was the ultimate reference frame, the silent partner to all action in the cosmos. He laid out this revolutionary idea in his monumental work, the Philosophiae Naturalis Principia Mathematica, often called the greatest scientific book ever written. In it, he defined absolute space as something that, in its own nature, without relation to anything external, remains always similar and immovable. This was a dramatic departure from earlier, more relational views. Distance in this new system was no longer just a comparison between two objects. It became an objective, measurable quantity within this absolute arena. You could, in theory, mark a point in this endless void and know it was truly at rest. This concept was the bedrock that allowed his law of universal gravitation to work with such stunning accuracy. The force between two objects depended on the distance between them, and thanks to absolute space, that distance was a real, dependable fact of the universe, not a matter of perspective. This framework was phenomenally successful. It allowed astronomers to predict the orbits of planets and the paths of comets with unprecedented precision. It gave engineers the tools to calculate the motion of everything from falling apples to cannonballs. By treating space as a real, physical entity with its own properties, Newton effectively made distance a fundamental character in the story of physics. It was the ruler by which the universe was measured, the grid upon which reality was drawn. For over 2 centuries, this view dominated scientific thought. It embedded itself so deeply in our understanding of the world that it became common sense. Of course, space is just there, a static stage. This notion that space itself is a foundational entity, a substance with objective reality, set the stage for all the physics that followed. It established a crucial precedent. To understand the universe, you must first understand the nature of the space it occupies, because distance is not an abstraction. It is a primary quantity from which everything else is built. Newton's absolute space, that fixed and immovable stage, stood unchallenged for over 2 centuries. It was a masterpiece of physics, a framework so powerful it felt like the final word on the subject. But then came a young patent clerk in Switzerland, armed with nothing but a powerful imagination and a deep faith in the laws of nature. Albert Einstein looked at Newton's perfect stage and saw something else entirely, not a rigid, silent container, but a dynamic, living fabric. His theory of relativity didn't just tweak Newton's ideas. It completely reinvented our understanding of the cosmos, weaving space and time together into a single, flexible entity called spacetime. In this new vision, distance was no longer a fixed, objective measurement. It became something fluid, something that could bend, stretch, and change, actively participating in the dance of the universe rather than just watching from the sidelines. The journey began with his special theory of relativity in 1905. Einstein started with 2 simple but revolutionary principles. The laws of physics are the same for all observers moving at constant speed, and the speed of light is always constant for everyone, no matter how fast they are moving. These 2 ideas led to some astonishing conclusions. Imagine 2 people, one on a speeding rocket ship and one standing still on Earth. If they both measure the distance between 2 points, they will get different answers. Length itself contracts for the moving observer. Similarly, they will disagree on how much time has passed between 2 events. Time dilates. This wasn't a trick of perception. It was a fundamental property of reality. Distance and duration lost their absolute status. They became relative, their values dependent on the motion of the person measuring them. The very ruler you use to measure the world changes its length based on how fast you are moving. Einstein had shown that space and time were not separate, independent entities. They were fused into a 4-dimensional continuum spacetime, and our experience of them was utterly malleable. But Einstein was just getting started. He spent the next decade grappling with a problem Newton himself had found vexing: how gravity could act instantly across vast, empty distances. How could the sun reach out across 93 million miles of nothingness to pull on the Earth? Einstein's brilliant insight was that gravity isn't a mysterious force at all. In his general theory of relativity, published in 1916, he proposed that mass and energy actually warp the very fabric of spacetime itself. Picture a taut rubber sheet. If you place a heavy bowling ball in the center, it creates a deep dimple. Now roll a marble across the sheet. It won't travel in a straight line. It will curve inward, orbiting the bowling ball as if pulled by a force. The marble isn't being pulled. It's simply following the curved geometry of the sheet. This is gravity. The sun's immense mass creates a curvature in space-time, and the Earth simply follows the straightest possible path through that curved geometry, which manifests as an orbit. What we feel as the force of gravity is really just us moving through the contours of warped space-time. This changes everything about how we see distance. In Einstein's universe, distance is not a passive backdrop. It is an active, dynamic player. It can be stretched and compressed. Near a massive object like a black hole, the distortion is so extreme that the distance between 2 points becomes radically different from what a distant observer would measure. Even the flow of time is tied to this geometry. A clock ticks slower deep within a gravitational well. This means that the path an object takes, the very motion we observe, is dictated not by invisible forces but by the underlying geometry of spacetime. The behavior of matter is governed by the shape of distance itself. Einstein's equations showed that this geometry isn't just influenced by matter. Matter and geometry talk to each other in a constant dialogue. The distribution of mass and energy tells spacetime how to curve, and that curvature, in turn, tells matter how to move. This was the final dismantling of Newton's absolute stage. There was no fixed reference point anymore, no privileged frame of rest. The universe became a shifting, evolving landscape where distance was a flexible concept. This profound shift opened a door to a much deeper possibility. If the geometry of spacetime, the arrangement of distances, is what ultimately dictates how everything moves and interacts, then perhaps distance is not just a property of the universe. Perhaps it is the primary substance from which the universe is built. Einstein's work suggested that what we perceive as solid matter might just be a manifestation of the twists and knots in this fundamental fabric, hinting that everything we see and touch might, at its heart, be nothing more than complex patterns in the dynamic relationships of space and time. Einstein's breathtaking vision of a dynamic, flexible spacetime was a monumental leap forward, but it was still, in a sense, a classical picture. It described a smooth, continuous fabric, like a perfectly woven silk sheet that could bend and curve. Yet, when physicists turned their attention to the impossibly tiny world of atoms and particles, they found that this elegant fabric doesn't just bend, it bustles and boils with a chaotic, unpredictable energy. This is the domain of quantum mechanics, a theory so strange it seems to rewrite the rules of reality itself. And when we apply its bizarre principles not to matter, but to the fabric of space-time, we arrive at one of the most radical ideas in all of physics, the concept of quantum foam. The man who gave this wild idea its name was the brilliant and charismatic physicist John Wheeler. In the 1950s, Wheeler was grappling with a fundamental conflict. Einstein's general relativity was a masterpiece of geometry, perfectly describing the large-scale universe of stars and galaxies. Quantum mechanics was an unparalleled success at predicting the behavior of the subatomic world. But the two theories were utterly incompatible. They spoke different mathematical languages and made contradictory assumptions about how the universe works. Wheeler realized that to marry these two giants, we might have to change our understanding of space and time at their very core. He proposed that if we could peer down to the smallest possible scale, the Planck length, which is a millionth of a billionth of a billionth of a billionth of a centimeter, the smooth, warped spacetime of Einstein would vanish. In its place, we would find a seething, turbulent frenzy. He called this frenzy quantum foam. Imagine the surface of the ocean on a calm day. From an airplane, it looks like a vast, smooth, blue plain. That's the spacetime of general relativity. But if you descend and get closer, you see waves and swells. Get closer still, and you see choppy, white-capped water. Now imagine shrinking down to the size of a single atom and looking at the surface of an individual water molecule. At that scale, it wouldn't look like a liquid at all. It would be a chaotic storm of particles jostling and vibrating violently. Quantum foam is like that. At the Planck scale, the concepts of here and there lose all meaning. Spacetime itself becomes a bubbling foam, with tiny wormholes constantly forming and collapsing, connecting different points in space and time for unimaginably brief moments. Virtual particles, pairs of matter and antimatter, spontaneously blink into existence from nothing, borrowing energy from the vacuum before annihilating each other and disappearing again, all in accordance with quantum uncertainty. This has a profound implication for our understanding of distance. In our everyday world, distance is a precise, measurable thing. We can say 2 points are exactly 1 meter apart. But in the quantum foam, this precision is an illusion. The very geometry of spacetime is subject to the same uncertainty principle that governs particles. We cannot know both the exact position and the exact momentum of a particle. The more we know about one, the less we know about the other. Wheeler suggested that at the Planck scale, this uncertainty applies to the fabric of spacetime itself. We cannot know the exact distance between 2 points with perfect accuracy. The closer we try to look, the more the measurement itself is disrupted by the frothing, fluctuating foam. The ruler we use to measure becomes part of the chaotic dance. This means that at its most fundamental level, space is not continuous and infinitely divisible, as Newton or even Einstein might have imagined. It is granular, it is pixelated, it is made of discrete, indivisible units. This idea that spacetime has a minimum size, a fundamental grain, is a direct challenge to centuries of scientific thought. It suggests that the smooth, continuous space we experience is an emergent property, a kind of average of this underlying chaos, much like the smooth appearance of a television screen emerges from millions of tiny, discrete pixels. What we perceive as empty distance is, in fact, teeming with unimaginable activity and structure. The void is not void at all. It is a vibrant, energetic plenum, a foundational layer of reality where the very concepts of space and time are born from a storm of quantum probabilities. This incredible insight pushes us to consider that distance itself might not be a primary, smooth backdrop, but something that is itself built from even more basic, granular units, the ultimate building blocks of everything. So if the fabric of spacetime is a churning quantum foam at the smallest scales, a seething ocean of uncertainty, then what are the fundamental entities that make up this foam? What is the source of this incredible turbulence? One of the most ambitious and mathematically elegant attempts to answer this question is string theory. This framework makes a breathtaking proposition. The most basic building blocks of nature are not zero-dimensional points like dots on a page, but unimaginably tiny, one-dimensional loops vibrating strings. To understand how this works, think of a guitar string. Pluck it, and it vibrates at a specific frequency to produce a particular musical note, say, a middle C. Pluck it differently, and it vibrates at a different frequency to produce a G. The string itself is the same. It's the mode of vibration that defines the note. String theory applies this same principle to the entire universe. It suggests that every single fundamental particle, electrons, quarks, photons, everything, is just a single type of string. The only difference between an electron and a quark is the unique vibrational pattern, the distinct note that its string is playing. In this symphony of the cosmos, the music itself creates the particles that build our reality. But there's a catch, and it's a monumental one. For the complex mathematics of this theory to produce the rich variety of particles and forces we observe in nature, these strings cannot simply vibrate in the three spatial dimensions we know: length, width, and height. The equations only work if the strings are vibrating in a universe with many more dimensions. Most versions of string theory require a total of 10 dimensions. That means beyond our familiar 3, there must be 6 additional spatial dimensions, all curled up and hidden from our everyday perception. Imagine a long, thin garden hose stretching off into the distance. From far away, it looks like a simple one-dimensional line, but if you get very close, you realize the hose has a second dimension, a circular cross-section that curls around its length. The 6 extra dimensions of string theory are thought to be curled up in a similar way, but into an incredibly complex, intricate shape called a Calabi-Yau manifold. These shapes are so tiny, compactified to the Planck scale, that we could never hope to see them directly. This is where the concept of distance becomes absolutely central in a whole new way. The geometry of these hidden dimensions, their size, their shape, the precise way they are curled up directly determines the possible vibrational modes of the strings. And since the vibrational modes define the properties of particles, the geometry of these unseen distances dictates the laws of physics themselves. The mass of an electron, the strength of the electromagnetic force, the charge of a quark, all these fundamental constants might not be arbitrary numbers, but are instead the inevitable outcome of the specific distances and shapes within these compactified dimensions. Change the geometry even slightly, and the strings would vibrate to a different tune, producing a universe with completely different particles and forces, a universe that might not be able to support atoms, stars, or life. In this view, distance is not just a measurement, it is the cosmic architect that writes the physical laws governing existence. Perhaps the most profound implication of string theory is its potential to finally resolve the century-old conflict between Einstein's smooth geometry of gravity and the chaotic uncertainty of quantum mechanics. In the standard model of particle physics, gravity is the stubborn outsider that refuses to play by the quantum rules. But in string theory, gravity emerges naturally. One particular vibrational mode of a closed string, a loop that connects back on itself, perfectly describes the particle that carries the gravitational force, the theorized graviton. This is a monumental achievement. It suggests that gravity, and by extension the very curvature of spacetime described by Einstein, is not a fundamental force but a consequence of strings vibrating in a higher dimensional arena. This leads to a truly mind-bending possibility. Spacetime itself might not be fundamental. The stage upon which everything plays might be an emergent property, a secondary effect that arises from the collective behavior of these vast networks of interacting strings and their relationships across multiple dimensions. If this is true, then the distance we measure in our three-dimensional world is merely a shadow, a projection of far more complex and intricate distances playing out in the hidden, compactified dimensions that form the true bedrock of reality. While string theory adds extra dimensions to weave its cosmic symphony, another powerful approach tackles the problem of quantum gravity from a completely different angle. Instead of building upon the idea of tiny vibrating strings, loop quantum gravity asks a much more direct and radical question. What if we stop thinking of spacetime as a smooth background and instead treat it as something that is itself made of discrete, quantized pieces? This theory doesn't add new dimensions or entities. It looks at the fabric of the universe and proposes that the fabric itself is woven from a network of finite, indivisible loops. It takes the quantum foam idea and gives it a precise mathematical structure, suggesting that space is not infinitely divisible, but is instead composed of tiny, fundamental grains. The core idea is to apply the principles of quantum mechanics directly to the geometry of spacetime. In the same way that light comes in discrete packets called photons, loop quantum gravity proposes that space comes in tiny, indivisible packets. The theory predicts that there is a smallest possible unit of area and a smallest possible unit of volume. You cannot have half a unit. These are the fundamental pixels of reality. This means if you tried to measure a smaller and smaller distance, you would eventually hit a limit, the Planck length beyond which the concept of shorter simply has no meaning. It's like trying to use a digital photo. You can zoom in only so far before you see the individual pixels, and you can't have half a pixel. Space itself is pixelated. So what are these pixels? The theory describes them in terms of spin networks, abstract webs of lines and intersections where each line carries a quantum of area and each node represents a quantum of volume. These networks are not embedded in space, they are space. The connections between these nodes define the geometry of the universe at the smallest scale. Think of it as the universe's most fundamental social network, where the relationships between points, the friendships, actually generate the experience of distance and separation. A region of space with a high density of these interconnected nodes would be a place of great volume, while a sparser network would correspond to less volume. The familiar, smooth space of our everyday experience emerges from this frenetic, underlying network of relationships, much like a smooth piece of fabric emerges from a complex weave of individual threads. This leads to a breathtakingly elegant view of the universe's evolution. The spin network doesn't just sit there, it evolves and changes over time. This evolution is described by spin foam, which is a history of the spin network's changes. A spin foam can be visualized as a series of interconnected spin networks, one for each moment in time, creating a complex, foamy structure that represents the entire history of spacetime. In this picture, the passage of time isn't about a clock ticking against a background. It's the result of this network continuously updating its relationships, transitioning from one state to the next. This provides a potential answer to one of the biggest mysteries: what happened at the Big Bang? In the loop quantum gravity framework, you can run the equations backwards, and instead of a singularity, a point of infinite density where the laws of physics break down, you find a big bounce. The immense gravity of the collapsing previous universe causes a repulsive force, reversing the collapse into the expansion we see today. This suggests our universe may have been born from the death of a previous one, with spacetime itself being reborn from the quantum network. Ultimately, loop quantum gravity presents a universe where distance is the most fundamental property of all, but not in the way we classically imagine it. Distance isn't a pre-existing void that things sit inside. It is a consequence of connection. It emerges from the relationships between the elementary grains of space. The space between your hand and your coffee cup is not empty. It is a vast, complex network of these quantum relationships, and the perceived distance is a manifestation of that network structure. This theory doesn't just quantize things in space, it quantizes space itself, offering a vision of reality where everything, every atom, every star, every one of us is quite literally built from the intricate web of these elementary spatial connections. This astonishing idea that our vivid three-dimensional reality might be nothing more than a magnificent projection from a two-dimensional surface finds its origins in one of the most enigmatic objects in the cosmos, the black hole. The story begins in the 1970s with a young physicist named Jacob Bekenstein and his legendary advisor, John Wheeler. Wheeler, ever the provocative thinker, posed a deceptively simple puzzle to his student. When an object falls into a black hole, it vanishes behind the event horizon, a point of no return from which not even light can escape. According to the fundamental laws of thermodynamics, entropy, a measure of disorder and information, can never decrease in a closed system. So Wheeler asked, what happens to all the information that describes that object, its atomic structure, its color, its mass? If it is truly lost forever, it would mean a catastrophic violation of one of physics' most sacred principles. Bekenstein took this paradox and turned it on its head. He proposed a revolutionary answer: the information isn't lost. Instead, it is somehow encoded on the surface of the black hole's event horizon. He argued that the entropy of a black hole, which is really a measure of its hidden information, is not proportional to its volume, as one might expect, but to the area of its event horizon. This was a staggering insight. Think of any ordinary object in your room, like a book. The information needed to describe that book, every word on every page, the texture of its cover, the type of glue in its binding, seems to be contained within its three-dimensional volume. But Bekenstein was saying that for a black hole, all the information about everything that has ever fallen into it is smeared across its two-dimensional surface. It's as if the entire contents of a library were not stored on shelves within the building, but were instead perfectly etched line by line onto the outside walls. This idea was later placed on a firm mathematical footing by Stephen Hawking, who showed through his work on quantum effects that black holes do indeed radiate energy and have temperature and entropy, cementing the profound link between gravity, quantum mechanics, and information theory. The holographic principle takes this black hole thermodynamics and boldly applies it to the entire universe. It suggests that Bekenstein's area law for information isn't just a quirky property of black holes, it might be a fundamental law of nature. The principle states that all the information contained within any volume of space can be fully described by a theory that resides on the boundary of that volume. To grasp how bizarre this is, imagine you are sitting in a room. Everything within that room, the air molecules, the dust motes dancing in a sunbeam, the very light and energy, is rich with information. The holographic principle asserts that a complete description of all that complexity, every single bit of data needed to perfectly reconstruct your three-dimensional reality, could be encoded on the two-dimensional walls, floor, and ceiling surrounding you. Our experience of depth, of volume, of distance between objects would then be a magnificent illusion, a holographic projection from the data stored on those surrounding surfaces. This transforms our understanding of distance from something fundamental into something that is emergent and derived. In this view, the space between two stars isn't a pre-existing emptiness they are sitting in. That vast three-dimensional gap is a manifestation of the information and the relationships defined on a distant two-dimensional surface. The farther apart two objects are in the projected three-dimensional world, the more complex the entanglement of the data points that represent them on the boundary. Distance becomes a measure of informational difference. It is not a primary ingredient of the universe, but a secondary quality that emerges from the processing of cosmic data. This is a concept that stretches the limits of intuition, proposing that the solidity of the world around us is as ephemeral as the image on a movie screen, which appears to have depth and motion, but is in reality just a flat surface illuminated by a carefully arranged stream of light and shadow. The implications of this are nothing short of metaphysical. If the holographic principle is correct, then the universe is not made of stuff located in space. It is made of information. Reality is fundamentally digital, a cosmic computation where the output is the immersive, three-dimensional experience we call existence. The distances we measure with telescopes and rulers are not the foundation of reality, but are themselves the product of a deeper, more abstract layer of description written on the outskirts of everything. It positions the universe as the ultimate hologram, a breathtakingly realistic projection built from nothing more than relationships and information encoded on the farthest edges of the cosmic horizon. If the holographic principle suggests our universe is a projection, a cosmic illusion of depth painted onto a flat surface, then we are left with a monumental question: what is the projector? What is the mechanism that translates that two-dimensional data into the rich, three-dimensional reality we experience every day? The most promising, and perhaps the most beautiful, answer to emerge from theoretical physics in recent years points to a phenomenon so strange that even Einstein famously dismissed it as spooky action at a distance: quantum entanglement. This bizarre connection between particles, where measuring the state of one instantly influences its partner no matter how far apart they are, might be the very glue that stitches the fabric of spacetime together, transforming abstract information into tangible geometry. To understand how this could possibly work, let's start with entanglement itself. Imagine you have a pair of magical dice. You take one die and travel to a distant galaxy, leaving the other here on Earth. The moment you roll your die in that far-off galaxy and it lands on, say, a 3, you instantly know that its partner back on Earth has also landed on a 3. This isn't just a prediction, it's a fundamental, instantaneous connection. The dice don't communicate, their fates are linked from the moment they are created. This is the essence of quantum entanglement. It creates a profound correlation between particles that defies our classical understanding of separation and local reality. Two entangled particles act as a single, unified system, even if they are separated by the entire breadth of the universe. They share a single existence, a single quantum state. Now, how do we get from this spooky connection to the very fabric of space? The breakthrough came when physicists like Mark van Romsdonk and others began to explore a fascinating thought experiment. They used the tools of string theory and quantum mechanics to ask what would happen to spacetime itself if they slowly turned down the amount of entanglement between two quantum systems. The result was astonishing. As they reduced the quantum entanglement, the geometry of the spacetime connecting those systems began to degrade. It was as if the very fabric of space was becoming stretched and thin, like pulling on a piece of taffy. If they reduced the entanglement all the way to zero, the spacetime itself would snap. A wormhole, a geometric bridge in spacetime, would literally pinch off and break, leaving two completely disconnected universes. This strongly implies that quantum entanglement is not just happening within space, it is what creates the geometric connection we perceive as space. The entanglement is the wormhole. The strength of the quantum connection directly dictates the robustness of the spatial geometry. This leads to an incredible idea often called "it from qubit," a play on physicist John Wheeler's famous phrase, "it from bit." A qubit is the basic unit of quantum information. The proposal is that the universe is fundamentally a vast network of entangled qubits, a cosmic web of quantum information. What we perceive as empty space is the manifestation of these entangled connections. The distance between two objects is not a fundamental void, but a measure of how deeply or shallowly their underlying quantum information is entangled. Two atoms that are close together in our experienced reality are, at the quantum information level, heavily entangled. Two distant galaxies have a much weaker, more indirect entanglement between their constituent bits. In this view, space doesn't contain relationships. Space is the relationship. It is the emergent property that arises from the complex pattern of quantum correlations. Think of it like this. Imagine the internet. The physical distance between two computers in different countries is largely irrelevant to their ability to communicate. What matters is their network connectivity, the routers, cables, and protocols that entangle their data. They can be physically far apart but informationally close if they are well connected. Emergent spacetime suggests our universe operates on a similar principle. The physical distance we measure with a ruler is a secondary effect, an emergent illusion that comes from the primary reality of quantum informational connections. The cosmos is not a collection of things in a void but a network of relationships, and from those relationships, the geometry of space and time spontaneously crystallizes. This means that the vast, three-dimensional expanse separating you from the stars is, at its most fundamental level, nothing more than a particular pattern of quantum entanglement, a cosmic tapestry woven from threads of spooky connection, giving rise to the beautiful and familiar geometry of our reality. This grand cosmic tapestry, woven from quantum entanglement and holographic information, finds its most breathtaking expression when we pull back to view the universe on its very largest scales. Here, in the realm of cosmology, distance is not a static measurement but the very language in which the history of the cosmos is written. Every observation we make of the distant heavens is a look back in time, and the vast gulfs between galaxies act as a timeline, chronicling the evolution of everything from a hot, dense beginning to the ever-expanding present. The key to deciphering this history lies in a simple but profound shift in the color of starlight, a phenomenon known as redshift. When astronomers point their telescopes at distant galaxies, they find the light from those galaxies is stretched. The specific wavelengths of light emitted by elements like hydrogen or oxygen are shifted toward the red, longer wavelength end of the spectrum. This isn't because the galaxies are physically red in color. It's because the fabric of space itself is expanding during the journey of that light across the cosmos. Imagine drawing a wave on a deflated balloon. As you inflate the balloon, the rubber stretches and the wave you drew gets longer. In exactly the same way as a photon of light travels for billions of years through an expanding universe, the space through which it moves stretches, elongating its wavelength. The greater the distance that light has traveled, the more space has expanded during its journey, and the more extreme its redshift becomes. This provides astronomers with a direct cosmic yardstick. By measuring the redshift of a galaxy, they can determine its distance from us and, by extension, how long its light has been traveling to reach our eyes. We are not just measuring empty space, we are measuring the cumulative effect of the universe's expansion over deep time. This relationship between redshift and distance was the crucial evidence that revealed our universe is not static but dynamically growing. It led to the monumental discovery of the cosmic microwave background radiation, the faint, cold afterglow of the Big Bang itself. This ancient light has been traveling for over 13 billion years, and its incredible redshift tells us the story of its epic journey. When it was first emitted, the universe was a searing hot plasma, and this radiation was energetic, short wavelength light. But as the universe expanded and cooled over eons, that light was stretched and stretched, its wavelength lengthening all the way into the microwave part of the spectrum. This is why we now detect it as a faint microwave signal coming from every direction in the sky. It is the most dramatic example of redshift imaginable, a direct echo of the primordial fireball whose light has been carried to us on the stretching fabric of space-time. its wavelength a testament to the vast distance and time that separate us from our origins. But the story of cosmic distance doesn't end with a simple, steady expansion. In the late 1990s, astronomers made a discovery so shocking it earned a Nobel Prize. The expansion of the universe is not slowing down, as everyone had assumed under the pull of gravity, but is actually accelerating. Galaxies are flying away from each other at a faster and faster rate. This breathtaking acceleration is attributed to a mysterious force dubbed dark energy, which seems to be an inherent property of empty space itself. And this is where the concept of distance becomes truly active and creative. Dark energy isn't just causing things to move apart within a fixed space, it is causing the space between galaxies to literally grow. New distance is being spontaneously generated in the vast voids between galactic clusters. It's as if the dots on our balloon are not moving apart because the balloon is being inflated, but because the rubber of the balloon itself is continuously being created between them. The very metric of space is evolving, stretching the cosmic landscape on which everything resides. This has a profound implication for the ultimate fate of the cosmos and solidifies the role of distance as a primary component of reality. An accelerating expansion driven by dark energy suggests a future where galaxies beyond our local gravitational group will eventually be pushed so far away by the relentless creation of new space that their light will never be able to reach us again. The universe will become a far more isolated and lonely place. The distances will become so vast that they are effectively infinite, severing the cosmic connections we see today. In this cosmological drama, distance is the lead actor. It is the ruler we use to measure the universe, the archive that stores its history in the light from distant objects, and the dynamic, evolving entity whose behavior, driven by dark energy, will ultimately determine the final fate of all that exists. The cosmos is not simply in space. It is being actively shaped and defined by the generative, creative power of distance itself. But if the expanding universe shows distance as an active, creative force, then black holes present its ultimate and most terrifying paradox. These cosmic anomalies are regions where the very fabric of spacetime is warped beyond all recognition, creating environments so extreme that our conventional understanding of distance doesn't just bend, it shatters completely. Imagine you are an astronaut on a fateful mission, falling feet first toward a stellar mass black hole. To a distant observer watching through a powerful telescope, your descent would appear to slow down dramatically as you approach the event horizon, the point of no return. You would seem to freeze in place, your image becoming increasingly reddened and dimmed by the intense gravitational field, almost as if you were painted onto the surface of the horizon, forever falling but never arriving. From that distant, safe vantage point, it looks as though the concept of reaching the black hole loses all meaning, because the space between you and the horizon seems to stretch into an infinite distance. Yet, from your own perspective inside the spacecraft, the experience is horrifyingly different. You would cross the event horizon without any dramatic flash or signpost, continuing your journey inward. But here, the normal rules of geometry are torn apart. In the universe outside a black hole, we can move freely in any spatial direction, but our movement through time is always forward into the future. Inside the black hole, due to the infinite curvature of spacetime predicted by general relativity near the singularity, the roles of space and time effectively swap. The relentless pull toward the center, the singularity, is no longer a place you can avoid moving toward. It becomes your inevitable future. Every possible path, every particle and light ray is dragged inexorably toward that central point. The direction toward the singularity becomes a moment in time that you are hurling toward, not a location in space you can choose to avoid. The very idea of distance to the center becomes meaningless because you are not traveling through space to get there. You are traveling through time to a moment of catastrophic destruction. This is where our physical theories reach their breaking point. General relativity describes the singularity as a point of infinite density where the curvature of spacetime becomes infinite, and our equations simply fail. Distances cannot be calculated, geometry ceases to exist. It's not just that we don't know what happens there, the tools we use to define here and there completely break down. This mathematical crisis is a powerful clue that Einstein's theory, for all its brilliance, is incomplete. It treats spacetime as a smooth, continuous fabric, but the insane physics of the singularity screams that this cannot be the final answer. This is where quantum mechanics must enter the picture to rescue us, and it does so with another astonishing idea about information and distance. The work of Stephen Hawking showed that black holes are not completely black. Due to quantum fluctuations near the event horizon, they slowly radiate energy and evaporate over astronomical timescales. This creates the infamous information paradox. If a black hole evaporates completely, what happens to all the information about the stars, planets, and unlucky astronauts that fell in? The laws of quantum mechanics insist that information cannot be destroyed. The potential solution that has gained tremendous traction is that the information is never actually lost inside the black hole. Instead, it is meticulously encoded on the event horizon itself. Just as the holographic principle suggests a universe's entire volume can be described by information on its boundary, a black hole's entire interior content might be described by quantum bits on its two-dimensional surface. This transforms the event horizon from a simple point of no return into the most important data storage device in the universe. The vast three-dimensional space inside the black hole, with its confusing and inverted laws of physics, may not be fundamental reality. It could be a projected illusion, a hologram emerging from the complex interactions of quantum information dancing on the surface of the horizon. If this is true, then the immense distance from the horizon to the singularity isn't a real physical gap. It is a manifestation of the depth and complexity of the information processing happening at the boundary. A black hole doesn't contain space, it is space generated from the correlations and entanglements of data on its surface. These cosmic monsters are not just destructive ends but could be the ultimate natural laboratories, forcing us to conclude that what we perceive as distance and separation is, in the most extreme conditions, a derived property emerging from something far more fundamental: information. Yet for all our sophisticated cosmic yardsticks and quantum theories, we are still bound by a fundamental constraint. We can only perceive and measure distance through a set of limited, imperfect proxies. Our entire experience of the space between things is built upon a foundation of light, time, and our own motion, each layer introducing its own unique form of subjectivity. Consider something as simple as seeing a tree across a field. You don't directly perceive the distance to that tree. Your brain brilliantly calculates it by comparing the slightly different images from your two eyes, a process called stereopsis. It uses shadows, the known size of objects, and how much the tree stands out against the background. This is an impressive biological feat, but it is also a constructed illusion, a best guess based on sensory inputs. This same principle of indirect measurement is magnified to an incredible degree when we look outward to the stars. We cannot stretch a tape measure from Earth to a distant galaxy. Instead, we rely on messengers, primarily light, to bring us information about the vast gulfs of space. Our entire cosmic distance ladder is built upon these clever but indirect tricks. For objects within our solar system, we might use radar bouncing radio waves off a planet and timing how long it takes for the echo to return. The delay, often just minutes, tells us the distance. For farther stars, we use the concept of parallax, much like your two eyes. We observe a star's apparent shift in position against the backdrop of much more distant stars from opposite sides of Earth's orbit around the Sun. A tiny shift of less than 1 arcsecond can reveal a star's distance. For galaxies millions of light years away, we depend on standard candles objects like certain types of supernova or variable stars whose intrinsic brightness we believe we know. By measuring how dim they appear to us, we can calculate how far away they must be. And for the most distant reaches of the observable universe, we measure the redshift of their light, interpreting the stretching of wavelengths as a direct proxy for the amount of space that has expanded during the light's multi-billion-year journey. Every single one of these methods is a workaround. We are not measuring distance itself, we are measuring time delays, angular shifts, brightness, and color, then using our physical theories to infer the distance. The map is not the territory. We are reading the shadows on the cave wall and trying to reconstruct the objects casting them. This inherent uncertainty is not just a practical limitation, it is woven into the very fabric of reality at the quantum level. Werner Heisenberg's famous uncertainty principle tells us that at the subatomic scale, there is a fundamental trade-off. The more precisely you try to pin down a particle's position, the less you can know about its momentum, and vice versa. This isn't a statement about the clumsiness of our measuring equipment. It is a fundamental property of nature. It means that a particle does not have a perfectly well-defined position and a perfectly well-defined trajectory at the same time. At these infinitesimal scales, the concept of a precise distance between two quantum particles becomes fuzzy and probabilistic. We can only speak of the probability of finding a particle at a certain location relative to another. The electron orbiting an atom's nucleus isn't like a planet in a neat orbit. It exists as a cloud of probability, a haze of potential locations. The distance from the nucleus is not a single number but a spread of possibilities. This forces us to ask a deeply philosophical question. If the most fundamental constituents of matter do not have definite positions, then can the distances between them truly be considered definite and real in the classical sense? Or is distance, at its core, a statistical and emergent property that only solidifies into something concrete when large numbers of particles interact? This challenge to the objective reality of distance extends beyond the quantum realm and into the very nature of observation. In both relativity and quantum mechanics, the act of measurement is not a passive reading of pre-existing facts. It is an interaction that can shape the outcome. In special relativity, as we've seen, two observers moving relative to each other will measure different distances between the same 2 points. There is no God's eye view that tells us which measurement is the true one. Both are equally valid within their own reference frames. The distance is not an absolute property residing in space. It is a relationship that depends on the state of the observer. This moves distance from being an intrinsic property of the universe to being a relative property that emerges from an interaction. It suggests that what we call reality is deeply connected to how we choose to look at it. We are not detached cartographers mapping a pre-existing landscape. We are participants in the cosmos, and the distances we measure are as much a reflection of our own place and motion within it as they are of some independent external world. So where does this leave us? It suggests that our everyday, intuitive sense of distance, the clear, objective gap between two objects, is a magnificent and very useful illusion. It is a highly effective interface that our brains and our science have developed to navigate the world. but it may only be the surface level of a far deeper and more mysterious reality. The way we measure and experience distance may be merely scratching the surface, pointing toward profound layers where separation is not fundamental but emergent, where vastness is born from information, and where the spaces between things are not empty but are the most active and creative elements of all. Our perception gives us a powerful and consistent reality, but physics hints that this reality is a beautifully rendered projection, and the true nature of distance is waiting to be uncovered in the quantum whispers between entangled particles and the holographic data on the boundary of the cosmos. This radical shift in perspective, where distance is not just a measurement but the very substance of reality, sends tremors through centuries of philosophical thought. For ages, the dominant worldview has been materialism, the belief that the fundamental stuff of the universe is matter. Atoms, quarks, electrons, these solid, tangible particles are what build rocks, trees, and people. Everything else, including the space they inhabit, is often seen as a secondary stage, a passive container. But if the theories we've explored hold weight, this hierarchy may be completely inverted. We are compelled to consider a universe where relationships are more fundamental than the things being related. What we perceive as solid, independent objects might instead be transient patterns, intricate knots, or stable vibrations within a vast, dynamic network of spatial connections. The object is not primary, the relationship is. The dancer is less real than the dance. This idea finds a powerful echo in a school of philosophy known as structural realism. Its proponents argue that what is truly fundamental and enduring about our scientific theories is not their description of specific objects, but their mathematical structure, the web of relationships and equations that describe how things interact. Think about it this way: over the centuries, our conception of the fundamental object has changed dramatically. We moved from the four classical elements to atoms, from atoms to protons and electrons, and from those to quarks and strings. The things keep changing, but what has remained remarkably consistent are the relationships described by mathematics, the laws of gravity, the principles of thermodynamics, the wave equations of quantum mechanics. Structural realism suggests that this is because the structure itself is the bedrock of reality. The things we see are just positions or nodes within that everlasting structure. In the context of our journey, this structure could be the geometry of spacetime, the network of quantum entanglement, or the informational relationships on a cosmic boundary. The distances and their interconnections are the permanent reality. The particles are just temporary manifestations. This forces us to confront one of the most ancient and puzzling concepts in both philosophy and physics: the nature of emptiness, the void. For materialists, empty space is truly nothing, a complete absence of matter and energy, a sheer void. But if distance is fundamental, then the void is not empty at all. It is the most real thing there is. It is the generative ground of being, the active field from which all forms temporarily arise. This is a view with deep roots, from the Taoist concept of the fertile void to the ancient Greek atomists who insisted the void was necessary for motion to occur. A modern physicist might call this the quantum vacuum, a seething sea of potentiality teeming with virtual particles and fluctuating energy. This isn't nothing. It is a something with definite properties and a complex structure. Emptiness, in this view, is not the absence of reality but its fullest expression. The solid objects within it are the illusions, the relatively stable whirlpools in the ever-flowing river of spatial relationships. Such a profound rethinking of ontology, the philosophical study of what exists naturally, leads to questions about our own place in this relational universe. If we are not collections of isolated atoms but rather complex patterns woven into a cosmic network of distance, what does that say about the nature of the self? Our sense of being a separate, bounded entity, distinct from the space around us, could be a biological and psychological simplification, a useful trick of the brain for navigating the world. The boundary of your skin might feel solid and definitive, but at a quantum level, it is a fuzzy, permeable interface where your particles are constantly interacting with the particles of the air, exchanging energy and information with the vast spatial network you are embedded within. You are not a statue placed in a room. You are more like a wave rising from the ocean. You have a distinct shape and form for a moment, but you are never truly separate from the watery medium that gives you existence. This perspective doesn't diminish our reality. It deepens it, connecting our individual consciousness to the fundamental fabric of the cosmos, suggesting that we are not merely in the universe, but that the universe is expressing itself through us as a pattern of relationships within the grand, dynamic interplay of distances. This journey from ancient philosophy to quantum foam and emergent spacetime reveals a universe where distance is active and creative, not a passive stage. But to fully grasp how something as seemingly abstract as empty space could be the foundation of everything, we must turn to the pure language of relationships itself, mathematics. For it is here, in the realm of abstract logic and precise definition, that we find the most compelling evidence that distance can exist entirely on its own, completely independent of any objects or stuff that might be used to measure it. Mathematics provides the tools to describe the architecture of reality using nothing but the concept of separation. Consider the simple, intuitive idea of measuring the gap between two trees with a ruler. Our everyday understanding is tied to those physical objects, the trees and the ruler. But mathematicians asked a far more profound question. What are the essential, unchanging properties of distance itself if we strip away all the physical context? The answer led to the creation of metric spaces, a foundational concept in mathematics. A metric space isn't a physical place. It's any set of points where we can define a distance function. This function is just a rule that takes any 2 points and gives a number representing how far apart they are. But for this rule to truly behave like distance, it must obey a few simple, intuitive axioms. The distance between a point and itself must be 0. The distance from point A to point B must always be the same as the distance from B to A. And perhaps most importantly, it must satisfy the triangle inequality. The direct distance from A to B can never be longer than going from A to C and then to B. What's astonishing about this is its sheer abstraction. The points in this set don't have to be locations in space. They could be numbers, functions, or even abstract symbols. The distance between them doesn't have to be measured in meters. It could be a measure of similarity, a difference in time, or a mathematical difference. This framework separates the pure concept of distance from any specific physical incarnation. It shows that distance is fundamentally a relational property between elements, a way of quantifying difference. This mathematical purity gives physicists a powerful toolkit. When Einstein described spacetime as a 4-dimensional manifold, he was essentially saying the universe is a type of metric space. The distance between two events in spacetime isn't just a spatial gap. It's a spacetime interval calculated using a specific rule, the metric tensor, that encodes both spatial separation and the flow of time between those events. The metric tensor is the heart of general relativity, and it is a perfect example of distance without stuff. It is a mathematical object that defines the geometry of spacetime at every point. If spacetime were perfectly flat and empty, the metric tensor would describe the familiar, rigid distances of Euclidean geometry. But where matter and energy are present, the metric tensor becomes complex and curved, dictating how distances are stretched and compressed. Crucially, this tensor field exists and has a value at every single point in spacetime, completely independently of whether there is a particle there to experience it. The geometry is the primary reality. It is the gravitational field itself. Matter then simply responds to the curvature defined by this field. This flips the traditional Newtonian view on its head. Instead of matter creating a force that acts across a distance, matter tells spacetime how to curve, and that curvature, that specific arrangement of distances, tells matter how to move. This mathematical perspective is pushed even further by the field of topology, often called rubber sheet geometry. Topology is concerned with the properties of space that remain unchanged when you stretch, twist, or bend it, but not tear it or glue it together. To a topologist, a coffee mug and a donut are the same shape because one can be continuously deformed into the other. They both have one whole. This field asks questions about connectivity and continuity without any concern for precise distances. Is a space simply connected, or are there holes? Is it finite or infinite? These are questions about the fundamental relationships between points that are even more basic than the metric that defines exact distances. Some theories of quantum gravity suggest that before the familiar metric of spacetime emerges, there is a more primordial topological phase, a frothing network of connections whose structure gives rise to distance itself. In this view, the metric tensor and the precise distances it defines are not the starting point but the final, classical outcome of a deeper, pre-geometric reality. Mathematics, in its most abstract forms, provides the language to describe a universe that is built not from substance, but from pure relationship, where distance is the fundamental variable from which everything else is derived. These mind-bending theories of a pixelated universe, from quantum foam to spin networks, are not just mathematical daydreams. They are testable hypotheses, and a global community of physicists is now devising incredibly clever experiments to go out and hunt for the first direct evidence that spacetime itself is granular. The challenge is almost unimaginable. The scale at which this graininess is predicted to appear is the Planck length, which is about 10 to the power of -35 meters. To put that in perspective, if you were to magnify a single atom to the size of the entire observable universe, the Planck length would be roughly the height of an average tree. We cannot build a microscope powerful enough to see something that small. So how do you look for the pixels of reality when they are fundamentally beyond the reach of direct observation? You look for their side effects. You search for tiny, telltale imperfections that this underlying graininess might imprint on the things we can measure. One of the most promising strategies is to use nature's own particle accelerators. When we look at light coming from incredibly distant astrophysical sources, like gamma-ray bursts or active galactic nuclei billions of light-years away, that light has been traveling across the universe for eons. According to some models of granular spacetime, the foamy, turbulent nature of space at the Planck scale should act like a subtle fog. It would cause very slight delays in the arrival time of photons depending on their energy. A high-energy gamma-ray photon and a lower-energy radio wave photon, both emitted at the same instant from the same violent cosmic event, should not travel at exactly the same speed through this quantum foam. The higher-energy photon, with its smaller wavelength, would be more sensitive to the minute bumps and wrinkles of the granular spacetime, potentially slowing it down by a tiny, almost imperceptible amount. This means that after a journey of 1 billion years, the two photons might arrive at our telescopes a fraction of a second apart. That delay is what scientists are desperately searching for. This is precisely the kind of work being done with instruments like the Fermi Gamma Ray Space Telescope. Fermi is designed to detect the highest energy light in the universe, gamma rays. By meticulously analyzing the arrival times of photons from distant gamma-ray bursts, physicists can look for these energy-dependent speed delays. The results so far have been both frustrating and thrilling. They have placed incredibly tight constraints on many models of quantum spacetime, effectively ruling out some of the simpler versions, but they haven't found the definitive signal yet. The universe is preserving its secret, but with every new gamma-ray burst that Fermi detects, we get a little bit closer to either seeing the graininess or being forced to rethink our theories entirely. It's a painstaking process of elimination, a cosmic game of hide and seek with the very fabric of reality. Another fascinating approach doesn't look out at the distant cosmos but right here on Earth, using incredibly precise laboratory experiments. If spacetime is granular, it might not be perfectly smooth and isotropic. It might have a preferred direction or a subtle grain, like wood. This could violate a fundamental symmetry of physics known as Lorentz invariance, which is the principle that the laws of physics are the same for all observers, regardless of their orientation or constant velocity. To test this, scientists use devices like ultra-precise optical resonators or atomic clocks. The idea is to see if the speed of light or the ticking rate of time changes ever so slightly as the Earth rotates on its axis and orbits the Sun, changing our direction of travel through this hypothetical grainy medium. It's like being on a ship and trying to detect the ocean's current by measuring if you move slightly faster when sailing with it than against it. These experiments are so sensitive they can detect distortions in spacetime 1 billion times smaller than an atom. So far, they too have found nothing, which is a powerful result in itself, telling theorists what kind of granular models are still possible. Perhaps the most dramatic way to probe these unimaginably small distances is to recreate the conditions of the early universe, and for that, we turn to the world's largest machine, the Large Hadron Collider. By smashing protons together at velocities approaching the speed of light, the LHC creates fleeting flashes of immense energy, condensing that energy into new particles. The hope is that at these extreme energies, we might not just create new particles, but actually briefly excite the fabric of spacetime itself. It's the difference between tossing a pebble into a still pond and setting off a depth charge. The pebble creates ripples on the surface. Those are like the particles we normally see. The depth charge might reveal the muddy bottom underneath the granular structure of spacetime itself. While the LHC hasn't found direct evidence for quantum gravity yet, every collision provides data that helps refine our understanding of what the quantum universe cannot be, steadily narrowing the path toward a final theory. These experimental quests represent a monumental shift in physics. For decades, the search for quantum gravity was largely a theoretical endeavor, a playground for mathematicians. But now it is becoming an observational science. We are no longer just asking, what must the universe be like? We are going out and demanding that the universe show us its cards. We are using the most violent explosions in the cosmos, the most precise machines ever built, and the most powerful colliders on the planet to answer one of the most profound questions ever posed. Is the smooth, continuous space we perceive just a beautiful illusion, a cosmic consensus that emerges from a hidden world of fundamental, granular units of distance? The experiments are running, the data is pouring in, and it is only a matter of time before they reveal the answer. While the quest to understand the fundamental nature of distance may seem like abstract theoretical physics, its most profound impact could be felt not in our textbooks, but in our daily lives, revolutionizing technology in ways that sound like pure science fiction. This shift in perspective, from seeing distance as a passive void to understanding it as an active, buildable entity, opens the door to engineering the very fabric of reality. The most immediate and tangible application of this is already unfolding in laboratories around the world: quantum computing. Traditional computers process information in bits, which are either zeros or ones. But quantum computers use qubits, which can be 0, 1, or both simultaneously, a state called superposition. This alone is powerful, but the real magic, the true engine of a quantum computer's unimaginable power, is quantum entanglement. Remember, entanglement creates a profound connection between particles where measuring one instantly defines the state of the other, regardless of the physical distance between them. In a quantum computer, we are not just using entanglement. We are actively harnessing the power of this spooky, distance-defying connection to perform calculations. By carefully entangling multiple qubits, we can make them work together on a problem in a way that is completely impossible for any classical machine. It's like having a team of mathematicians who aren't just working in parallel, but who are all sharing the same thoughts simultaneously across a vast, interconnected network. This allows a quantum computer to explore a near-infinite number of possible solutions to a problem at once, promising breakthroughs in designing new life-saving medicines, creating ultra-efficient materials, and cracking complex logistical puzzles that currently stump our most powerful supercomputers. We are not just building faster calculators, we are building machines that leverage the very nature of quantum-connected distance to process information. But what if we could go beyond information and manipulate the geometry of spacetime itself for transportation? This is the realm of the theoretical warp drive, a concept that has been lifted from the pages of Star Trek and into the pages of serious physics journals thanks to the work of theorists like Miguel Alcubierre. The principle is breathtakingly simple in concept, yet fiendishly complex in practice. The Alcubierre warp drive doesn't propose propelling a ship through space at impossible speeds, which would violate relativity. Instead, it suggests a way to manipulate the distance around the ship. Imagine a surfboard on the ocean. The surfboard itself isn't moving through the water, the wave is carrying it. The warp drive concept is similar. It would involve creating a bubble of flat spacetime around a spacecraft. In front of the ship, the drive would compress spacetime, literally bringing the destination closer. Behind the ship, it would expand spacetime, pushing the point of origin farther away. The ship inside this bubble would remain motionless in its local space, not experiencing any crushing g-forces, while the space itself moves, effectively allowing the vessel to ride a wave of distorted geometry. This wouldn't be travel through space, it would be travel of space. The mind-bending implication is that the speed of light limit, which applies to motion within spacetime, might not apply to the expansion and contraction of spacetime itself. While the energy requirements and exotic materials needed are currently far beyond our reach, the very fact that such an idea is being seriously explored by physicists shows how viewing spacetime as a malleable medium, rather than a fixed stage, completely changes what we believe is possible. Perhaps the most startling evidence that we are already learning to engineer the properties of space comes not from distant futures or massive particle colliders, but from the field of metamaterials. These are not metals mined from the Earth, they are artificially structured materials engineered at a microscopic level to have properties not found in nature. By carefully designing the shape, geometry, size, and arrangement of these nanostructures, we can literally dictate how light and other electromagnetic waves travel through them. This has led to the creation of the first functional invisibility cloaks. How do they work? They don't make an object transparent. Instead, they guide light waves around the object, like water flowing around a smooth rock in a stream. To an observer, the light waves arrive completely undisturbed, making it appear as if the object and the space it occupies simply aren't there. This is a direct, controlled manipulation of the path that light takes, a manipulation of the effective distance that light travels around an object. We are not just bending light, we are bending space, or at least creating a material analog that perfectly mimics that effect. This technology is in its infancy, but its potential extends far beyond hiding objects. It could lead to revolutionary lenses that see details far smaller than the wavelength of light, or to coatings that make buildings invisible to seismic waves, protecting them from earthquakes. These metamaterials are a physical proof of concept, a demonstration that by understanding the geometry of paths and distances, we can create effects that once belonged solely to the realm of fantasy. The ultimate application, however, might be the most profound of all, tapping into the energy of spacetime itself. If the quantum vacuum is truly a seething foam of virtual particles flashing in and out of existence, as quantum field theory suggests, then empty space is not empty at all, it is a vast reservoir of fluctuating energy. The Casimir effect provides a tiny glimpse of this. When you place two incredibly smooth, uncharged metal plates extremely close together in a vacuum, they are gently pulled toward each other. Why? Because the space between the plates is so narrow that only certain wavelengths of virtual particles can flicker into existence there, while outside the plates, all wavelengths can appear. This creates a pressure difference that pushes the plates together. We are seeing, in a very subtle way, the energy of the vacuum itself exerting a force. The monumental challenge is to find a way to extract useful energy from this vacuum flux on a larger scale. If spacetime is emergent from a more fundamental network, as theories like loop quantum gravity suggest, then perhaps one day we could learn to interact with that underlying layer, not unlike how we learn to harness the flow of electrons. This wouldn't be creating energy from nothing. It would be tapping into the fundamental activity of the spatial network that constitutes the universe. The technologies born from this new understanding of distance promise a future where we don't just live in space, but where we learn to work with it, shaping it to overcome the greatest challenges in computing, transportation, and energy. Long before physicists began to mathematically formalize the nature of space, artists were already conducting their own profound experiments, using canvas and pigment to dissect and redefine our perception of distance. The Renaissance invention of linear perspective was nothing short of a revolution in visual reality. Pioneered by figures like Filippo Brunelleschi and Leon Battista Alberti, this technique used mathematical principles to create the illusion of depth on a flat surface, converging parallel lines at a single vanishing point on the horizon. For the first time, a painting could become a window into a coherent, measurable world. This was more than an artistic trick. It was a philosophical statement that space was rational, orderly, and could be mastered by human intellect and observation. The canvas became a controlled laboratory for exploring spatial relationships, imposing a geometric structure on the chaos of visual experience and suggesting that distance itself was a fundamental dimension that could be precisely quantified and beautifully rendered. This artistic interrogation of space continued to evolve, fracturing and reassembling in the 20th century with movements like Cubism, where Renaissance art sought to create a perfect window onto a coherent world. Picasso and Braque shattered that window into 1,000 pieces. A Cubist painting presents its subject a person, a guitar, a bottle from multiple viewpoints simultaneously, as if the artist had walked around it and captured every perspective at once, then fused them onto a single canvas. This was a radical rejection of the single, fixed vantage point that had dominated for centuries. It proposed that space is not an absolute container observed from one location, but a relativistic experience that depends entirely on the observer's position and movement. Cubism, in its own intuitive way, was grappling with ideas that would soon emerge in Einstein's physics, suggesting that there is no single, privileged perspective from which to measure the world, and that reality is a complex synthesis of many different viewpoints and distances intertwined. The literary world has been just as consumed with the puzzle of spatial reality, often using it as a direct metaphor for the landscapes of the human mind. Perhaps no work captures this more brilliantly than Jorge Luis Borges' short story, The Library of Babel. Borges imagines a universe that is literally a limitless library, composed of an infinite number of hexagonal galleries. Each gallery contains a set number of books, each book has a set number of pages, and each page is filled with a seemingly random arrangement of letters. The librarians who inhabit this universe are consumed by the desperate belief that somewhere in this infinite expanse of textual space, there must exist books that contain all knowledge, the perfect book that explains everything, the catalogue of all catalogues, the story of your own death. Borges' library is a breathtaking metaphor for a spatially infinite and informational universe. The physical distance between the galleries becomes a measure of informational difference. The despair of the librarians stems from the terrifying vastness of it all. The answers they seek might exist, but the sheer, unimaginable distance they would have to travel to find them makes the search utterly futile. It is a profound artistic premonition of the holographic principle, where the universe is seen as a vast store of information, and the space we navigate is merely the physical manifestation of that data's arrangement. Science fiction, as a genre, has served as a popular playground for testing the limits of spatial connection and separation. The concept of the wormhole, a shortcut through the folded fabric of spacetime, is a staple trope that allows characters to traverse interstellar distances in an instant. But more than just a convenient plot device, the wormhole is a narrative embodiment of humanity's deepest desire to overcome isolation, to connect what is separate, and to make the vast, cold emptiness of space feel intimate and navigable. It represents a hope that the universe's geometry might ultimately be friendly to our need for community and exploration. Similarly, tales of alternate dimensions or parallel universes explore the idea that the space we perceive is not the only space that exists. There could be entire realities separated from us by an unimaginably tiny distance in a higher dimension, forever just out of reach. These stories allow us to emotionally grapple with the possibility that our familiar three-dimensional world is a tiny slice of a far richer, more complex cosmic architecture, giving us a narrative framework to understand the hidden dimensions of string theory long before we encounter the mathematics. From the precise grids of Renaissance masters to the folded geometries of sci-fi wormholes, these cultural expressions are far more than mere entertainment or decoration. They are a vital part of humanity's ongoing conversation about the nature of reality. They provide the emotional and philosophical vocabulary for concepts that can often feel cold and abstract when presented in equations. Art gives us a way to feel the weight of infinity, to experience the disorientation of relativistic space, and to confront the haunting possibility that our world is built upon a foundation of information. They remind us that the mystery of distance is not just a problem for physicists to solve with particle accelerators and telescopes. It is a fundamental part of the human condition, a source of both terror and wonder that has always been, and will always be, explored with every tool at our disposal, whether it's a painter's brush, a writer's pen, or a filmmaker's camera. Of course, not every physicist is ready to embrace the idea that distance is the fundamental bedrock of reality. For many, this radical perspective feels like putting the cart before the horse. The traditional and still deeply compelling view is that matter and energy are the primary substances of the universe. In this framework, particles with mass and charge are the undeniable, concrete things we can detect and measure. Space, then, is simply the passive arena they inhabit, the necessary void that allows for their existence and interaction. To suggest that this void is more real than the particles themselves strikes some as a philosophical step too far, an abstraction that risks losing touch with the tangible stuff that actually constitutes our world. These critics would argue that we are mesmerized by the stage and forgetting about the actors who bring the play to life. After all, it is the properties of matter, the mass of the electron, the charge of the proton, that dictate the laws of physics and the forces that shape our reality. To claim that these properties themselves emerge from spatial relationships can feel, to its detractors, like a clever mathematical trick that explains everything and nothing at the same time. A more substantial criticism, one that even proponents of emergent spacetime take very seriously, is the stark lack of direct experimental evidence. The theories we've explored, from string theory's extra dimensions to loop quantum gravity's spin networks, are breathtaking in their mathematical elegance and conceptual ambition. But for now, they remain largely in the realm of profound speculation. They have yet to make a specific, testable prediction that has been confirmed by observation or experiment. The search for quantum foam with gamma-ray telescopes or violations of Lorentz symmetry in ultra-precise labs has so far come up empty. This doesn't mean these ideas are wrong. It simply means they are not yet fully formed scientific theories in the same way that general relativity or quantum electrodynamics are. Critics rightly point out that a theory that cannot be falsified, that does not make clear predictions we can go out and look for, risks becoming a kind of metaphysical philosophy rather than hard science. The burden of proof lies with those proposing this new paradigm, and until a definitive experimental signature is found, the conservative view that spacetime is a fundamental continuum will understandably retain its powerful grip on the mainstream. Beyond these criticisms, there are also compelling alternative frameworks that propose a completely different starting point for reality. One of the most fascinating is causal set theory. This approach makes a bold claim. What is truly fundamental is not space or even space-time, but the mere concept of cause and effect. The theory proposes that the universe is built from a vast collection of discrete, individual events. The only thing that matters is the causal relationship between these events, whether one event can influence another. If event A can send a signal to event B, then we say A is in the causal past of B. This web of causal connections creates a kind of cosmic ancestry, a network of before and after. From this sparse, minimalist starting point, just events and their causal order, the theory aims to reconstruct everything else. The smooth, four-dimensional spacetime of our experience, with its distances and durations, is argued to be a large-scale approximation that emerges from this underlying network of causal links. In this view, time and its ordering are not emergent properties. They are the primitive, fundamental facts. Space and distance are the secondary concepts that crystallize out of the deeper causal structure. It's a stark reminder that our intuitive sense of geometry might not be the final word, and that the true architecture of the universe could be built on a foundation of pure process and relationship rather than extended substance. These robust criticisms and compelling alternatives are not a weakness in the scientific process. They are its greatest strength. The fact that such a profound debate is still raging at the frontiers of physics is a testament to the depth of the mystery we are confronting. It ensures that no single idea gains a monopoly without being rigorously stress-tested from every possible angle. This intellectual friction is what prevents groupthink and drives discovery forward. The question of whether distance is the builder of everything or merely a property of the things that are built remains one of the most open and exciting questions in all of science. Engaging with these counterpoints doesn't diminish the allure of the emergent spacetime idea. It enriches our exploration, forcing us to sharpen our arguments, seek better evidence, and remain humble in the face of a universe that continues to defy our simplest intuitions. This healthy, vibrant controversy is the engine of progress, pushing us toward a deeper and more complete understanding of the cosmic order. Think about the last time you looked at a perfect snowflake or the intricate pattern of a spider's web. There's something deeply satisfying about that kind of order, a sense that everything is in its right place. This intuitive appeal to harmony and balance isn't just a human preference. It is woven into the very laws of the universe through the powerful concept of symmetry. In physics, symmetry is far more than just a pleasing arrangement. It is a fundamental principle that dictates how reality operates, and it is inextricably linked to the very nature of the space we inhabit and the distances we measure. At its core, a symmetry in physics is a change that leaves a situation unchanged. Rotate a perfect sphere by any amount, and it looks exactly the same. Slide a perfectly flat, infinite plane in any direction, and its appearance is utterly unaltered. These are examples of profound symmetries in space itself, rotational invariance and translational invariance. They imply that the laws of physics don't have a favorite direction or a special location. The universe has no center and no preferred axis. This isn't just a philosophical statement. It has direct, observable consequences for how everything moves and interacts. The profound connection between these spatial symmetries and the measurable world was crystallized in one of the most beautiful theorems in all of physics, formulated by the brilliant mathematician Emmy Noether in the early 20th century. Noether's theorem is a cornerstone of modern theoretical physics, and it provides a stunningly elegant link between the abstract geometry of space and the concrete conservation laws we observe. The theorem states that for every continuous symmetry in nature, there is a corresponding conservation law. That is, for every transformation that can be applied smoothly without changing the physics of a system, there is a quantity that remains constant, forever unchanged. The implications are breathtaking. The translational symmetry of space, the fact that the laws of physics are the same here as they are a million light years away, directly leads to the conservation of momentum. Because space is uniform, an object's momentum cannot simply vanish. It must be transferred. The rotational symmetry of space, the fact that there is no privileged direction, leads directly to the conservation of angular momentum. A spinning ice skater pulls her arms in and she spins faster, but the total angular momentum remains perfectly constant, a direct result of the rotational symmetry of the space she's spinning within. This forces a radical shift in how we view the building blocks of reality. We often think of particles and forces as the primary entities, with conservation laws being helpful rules they follow. But Noether's theorem suggests we might have it backwards. The conservation of momentum and angular momentum aren't just rules, they are inevitable, emergent properties of the symmetrical nature of space itself. If distance is a fundamental, active component of the cosmos, as we've been exploring, then these deep symmetries might not be laws imposed upon the universe, but rather inherent properties of the spatial network from which everything is built. The uniformity of space gives rise to the conservation of momentum. The isotropy of space, its sameness in all directions, gives rise to the conservation of angular momentum. In this view, the very constancy we see in the motion of planets and particles, is a direct reflection of the symmetrical structure of the spatial stage. The stage itself possesses a kind of perfect harmony, and the actors, matter and energy, are compelled to move in ways that respect and reflect that foundational harmony. This relationship becomes even more fascinating when we consider what happens when symmetries break. We see this all around us in phase transitions. Consider a perfectly symmetrical, uniform magnetic material heated to a high temperature. Its atoms are jiggling wildly, and their magnetic poles are pointing in every possible random direction. The system is highly symmetric. Rotate it, and its overall magnetic state looks the same because there is no net order. But as it cools down, something remarkable happens. Suddenly, the atoms spontaneously choose a direction. They align themselves, and the material develops a north and south pole. The perfect rotational symmetry of the high-temperature state has been broken. The system has chosen a preferred axis. This isn't a destruction of symmetry, but a hiding of it. The underlying laws are still symmetrical, but the stable state of the system is not. This process of symmetry breaking is responsible for the existence of everything from the diversity of subatomic particles to the formation of galaxies in the early universe. Now apply this concept to the nature of space itself. If the fabric of spacetime emerges from a more fundamental network, as theories like loop quantum gravity suggest, then the smooth, symmetrical space we experience could be the result of a phase transition from a more chaotic, pre-geometric state. The vast, uniform vacuum we see today, with its perfect translational and rotational invariance, might be a frozen, low-energy state, a kind of cosmic ice. The symmetries that give us our cherished conservation laws would then be emergent properties, not fundamental ones. They would be the result of the spatial network settling into a highly ordered, stable configuration. This perspective suggests that the very constancy of distance and the reliability of our measurements are not a given, but a contingent property of our universe's current, cooled-down state. It opens up the incredible possibility that in the extreme heat of the Big Bang, or in the depths of a black hole, these symmetries might temporarily break down, and with them, our very notions of consistent distance and unbreakable conservation laws could become fluid and unpredictable, revealing a more complex and turbulent layer of reality beneath the calm, symmetrical surface we know. But if the symmetries of space give rise to the very laws that govern motion, then what is the nature of this space itself? Is it truly an inert void, or does it possess a hidden, vibrant energy all its own? To answer this, we must venture into the bizarre and counterintuitive world of quantum field theory, which presents us with one of the most startling revelations in all of physics. What we call empty space is not empty at all. In fact, it is a seething, bubbling cauldron of frantic activity. According to the rules of quantum mechanics, the vacuum of space is not a state of nothingness but the lowest possible energy state of a field. And at this level, the universe operates under a permanent state of uncertainty. This means that fields cannot sit perfectly still at zero. They must constantly fluctuate. These quantum fluctuations are not just mathematical abstractions. They manifest as pairs of virtual particles, a particle and its antiparticle spontaneously blinking into existence everywhere all the time. This astonishing process is often described as particles borrowing energy from the vacuum to briefly exist, before they inevitably collide and annihilate each other, paying back the energy loan in an unimaginably short span of time. These are not particles in the traditional sense that we can directly detect. They are called virtual precisely because they are fleeting ghosts, observable only through their indirect effects on the world. This isn't a rare event. It is happening in every single cubic centimeter of space around you right now. The void between the stars, the air in your room, even the space between the atoms in your own body, all of it is teeming with this chaotic dance of creation and destruction. The vacuum is alive, a dynamic medium far removed from the static nothingness of classical physics. The energy contained within this quantum frenzy is known as vacuum energy, and it has a direct, measurable consequence on the largest scales imaginable, the fate of the entire cosmos. When physicists first calculated the theoretical value of this vacuum energy density, they arrived at a number so catastrophically large that it would have caused the universe to expand apart with such violence that not even atoms could have formed. The fact that we exist at all means this calculated value must be wrong. The observed expansion of the universe, driven by what we call dark energy, requires a vacuum energy value that is about 120 orders of magnitude smaller than the naive theoretical prediction. This staggering discrepancy, known as the cosmological constant problem, is arguably the single greatest unsolved puzzle in fundamental physics. It tells us that something profound is missing from our understanding, that the energy of nothingness is a central player in the cosmic drama, influencing the expansion rate of the universe and ultimately determining whether it will end in a heat death or a big rip. Crucially, the behavior of these virtual particles is deeply tied to the concept of distance. The probability of a virtual particle pair appearing and the specific properties it might have is governed by the range over which it can interact. This is where the famous Casimir effect provides a stunningly elegant demonstration. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum, only a few nanometers apart. Normally, the quantum vacuum allows for virtual particles of all wavelengths to flicker in and out of existence. But in the narrow gap between the plates, only those virtual particles whose wavelengths fit perfectly between the plates can appear specifically, wavelengths that are fractions of the gap distance. Outside the plates, all wavelengths are possible. This difference in the number of possible virtual particles creates a pressure imbalance, with more activity pushing on the outer surfaces of the plates than on the inner surfaces. The plates are gently but measurably pulled together. This isn't some exotic force, it is a direct, laboratory-verified result of the quantum vacuum structure. The distance between the plates directly dictates which virtual particles can contribute to the vacuum energy in that region, proving that the properties of this nothingness are not constant but depend critically on spatial boundaries and dimensions. This incredible vacuum activity forces a complete revision of what we mean by emptiness. It implies that space itself is a structured medium, brimming with energy and potential. The distance between 2 points is not just a passive gap to be traversed, it is an active field of quantum potentiality, its character shaped by the fluctuations happening within it. This supports the profound notion that what we perceive as sheer nothingness is, in reality, a dynamic web of spatial relationships. The vacuum is not a blank slate but a physical system with its own properties, and the distances we measure are integral to defining those properties. The void is not void. It is the most richly textured thing there is, a foundational sea of energy and information from which all particles and forces emerge, making distance a key and active factor in the quantum processes that underpin our very reality. We all feel the relentless one-way flow of time in our lives. Eggs scramble but never unscramble, memories are made but never unmade. This irreversible directionality is known as the arrow of time, and it is one of the most persistent mysteries in physics. The laws of physics themselves, at their most fundamental level, are almost entirely time-symmetric. The equations governing particles work just as well if time runs forward or backward. So why does our lived experience point so definitively in one direction? The answer to this profound puzzle may be found not in the nature of particles or forces, but in the behavior of space itself and the ever-increasing distances that define our expanding universe. The most compelling and universal arrow of time we can identify is the cosmological arrow, defined by the expansion of the universe. As we look out into the cosmos, we see galaxies racing away from us, their light stretched and reddened by the relentless growth of the space between them. This isn't a motion through a static void. It is the void itself, the fabric of spacetime, that is actively stretching. This expansion provides a clear, unambiguous direction for time. If we could run the cosmic film in reverse, we would see all those galaxies rushing together, the space between them contracting, until everything converges to a hot, dense singularity, the Big Bang. The forward direction of time is inextricably linked to the increasing scale of the universe, to the generation of new distance. Without this expansion, we would lose the most fundamental reference point for time's arrow, suggesting that the flow of time might be a direct consequence of the stretching of space. This cosmic direction finds a powerful echo in the second law of thermodynamics, which states that the entropy or disorder of a closed system always increases over time. Think of a drop of ink falling into a glass of water. It starts as a concentrated, ordered blob, but it inevitably spreads out, dispersing evenly throughout the water, maximizing its disorder. It never spontaneously gathers itself back into a neat drop. This increase in entropy is the reason why we remember the past but not the future, and it defines the thermodynamic arrow of time. But notice the language we use. The ink spreads out. It occupies a larger volume. Its increase in entropy is directly tied to its ability to explore more possible configurations across a greater spatial distance. The drive toward higher entropy is fundamentally a drive toward occupying more space, toward spreading out and filling the available volume. In this way, the thermodynamic arrow is intimately connected to the geometry of the universe. The ever-increasing amount of space made available by cosmic expansion provides an ever larger playing field for entropy to increase, essentially giving disorder more room to grow and locking in the one-way direction of time. This leads to a truly profound speculation. What if time itself is not a fundamental entity, but an emergent property that arises from the evolution of spatial relationships? This idea turns our classical intuition completely on its head. We usually think of space as a static stage and time as the dynamic river flowing through it. But what if the river is an illusion? In this view, the fundamental reality is a vast, unchanging network of connections like the spin networks of loop quantum gravity. What we perceive as the passage of time is actually just our conscious experience of moving through a sequence of these frozen spatial states, much like flipping through the pages of a book. Each page is a single, static configuration of the universe's spatial relationships. The sensation of time passing is the process of updating from one page to the next. The arrow of time, then, would be the direction in which these updates happen, likely driven by the increasing complexity of these spatial connections as the universe expands. If this is true, then distance is not just a spatial concept. It becomes the very engine of temporal flow. The growth of the universe, the creation of new distance between galaxies, is what drives the system from one state to the next, providing the direction for change. The increasing separation of matter and the dilution of energy that comes with expansion might be the primary process that allows entropy to increase and gives time its irreversible direction. This would mean that the distinction between space and time, so central to Einstein's relativity, might blur at an even deeper level. Time would not be a separate dimension woven with space into a static four-dimensional block. Instead, it would be a secondary quality that emerges from the changing geometry of the spatial dimensions. The apparent flow of time would be a direct consequence of the universe's spatial structure evolving, with distance acting as the fundamental variable that dictates the pace and direction of this cosmic evolution, weaving together the fabric of reality from the simple, profound concept of separation. For centuries, physics seemed to present a fractured view of reality, with different forces governing different domains. Gravity ruled the cosmos, electromagnetism orchestrated light and chemistry, and the strong and weak nuclear forces held the atomic nucleus together. They appeared as separate, fundamental commands of nature. But what if this separation is just an illusion, a trick of perspective that depends entirely on the scale at which we're looking? This is the breathtaking promise of unified field theories, which propose that all these forces are actually different faces of a single, underlying superforce, and the key to seeing this unity is to understand the profound role that distance plays in shaping reality itself. The journey toward unification began in the 19th century with a monumental achievement. James Clerk Maxwell showed that electricity and magnetism, once thought to be distinct phenomena, were two aspects of a single electromagnetic force. This was our first glimpse of a deeper harmony. Then, in the 20th century, the standard model of particle physics achieved another stunning unification, describing how the electromagnetic force and the weak nuclear force responsible for radioactive decay merge into a single electroweak force at incredibly high energies. This was a crucial clue. The forces don't just exist independently. Their apparent strength and even their very identity depend on the energy, and therefore the distance at which we observe them. To understand this, imagine observing a city from different altitudes. From an airplane cruising at 30,000 feet, the intricate network of streets and neighborhoods blends into a single, unified metropolitan area. You can't see the boundaries between districts. They all appear as part of one connected whole. This is the view of the universe at extremely high energies and unimaginably tiny distances, like those that existed just moments after the Big Bang. At this scale, the forces are unified, but as you descend in your airplane, details emerge. At 10,000 feet, you start to see the major highways dividing the city into large sections. Then at 1,000 feet, individual streets, parks, and buildings become visible. The unified city you saw from high up now appears as a collection of distinct, separate neighborhoods. This is exactly what happens as the universe expands and cools. The energies drop, and the single unified force begins to freeze out into the distinct forces we recognize today. The strength of each force is not a fixed constant but a value that changes with the energy scale, which is directly related to the distance over which the force is acting. Grand unified theories take this idea even further, attempting to merge the electroweak force with the strong nuclear force into one grand framework. These theories predict that at the staggering energy levels found at a distance of about 10 to the negative 30 meters, a million billion times smaller than a proton, these three forces would have identical strength. They would be truly unified. This suggests a stunning reality. The reason we experience four separate forces is simply because we live in a cold, spacious universe. We are like observers on the ground, only able to see our own neighborhood, completely unaware that from a higher perspective, everything is connected. The variation of force strength with distance isn't a complication. It's a cosmic Rosetta Stone, allowing us to decode the hidden unity beneath the apparent diversity of nature's laws. The final and most elusive piece of this puzzle is gravity. Einstein's general relativity describes gravity not as a force in the traditional sense, but as the curvature of spacetime itself, a geometric property. The other forces are described by quantum field theory, which treats them as exchanges of particles within a fixed spacetime background. This is a fundamental incompatibility. Is spacetime the stage or one of the actors? Theories of everything, most notably string theory, aim to resolve this by bringing gravity into the fold. They propose that at the deepest level, even gravity is quantized and unified with the other forces. In this ultimate vision, the geometry of spacetime, the very definition of distance, isn't a passive backdrop but an emergent property that arises from the same underlying principles that govern particles and forces. The metric tensor that describes the curvature of space and the fields that describe the other forces would all be different vibrations of the same fundamental strings or different manifestations of the same quantum information. This grand pursuit elevates distance from a simple measurement to the ultimate unifying parameter, a single variable that bridges the chasm between the quantum world and the cosmos, between the very small and the very large. By dialing the cosmic distance scale, we can watch the forces transmute from one into another, revealing their common origin. It suggests that the architecture of reality is not built from multiple, independent blueprints, but from a single, elegant design where distance itself is the master key that unlocks the connections between all things, hinting that it may be the most fundamental ingredient in the recipe for the universe. This idea that the universe's physical laws might be uniquely suited for life finds its boldest expression in what's known as the Anthropic Principle. It's a simple but profound statement. The universe we observe must be compatible with the existence of observers. We shouldn't be surprised to find that the constants of nature seem finely tuned for our existence, because if they weren't, we wouldn't be here to notice. This isn't a claim about purpose or design. It's a recognition of a fundamental selection effect. We are not impartial viewers of the cosmos. We are products of its specific conditions, and our very presence filters the kind of universe we can possibly see. When we apply this lens to the concept of distance, we uncover a breathtaking series of cosmic coincidences that suggest the scales of space are not arbitrary numbers, but are, in fact, deeply woven into the possibility of life itself. Consider the very building blocks of matter, the atom. The size of an atom and the distances between its nucleus and electrons are governed by a delicate balance of forces. The strength of the electromagnetic force, which attracts the negatively charged electron to the positively charged proton, is precisely counterbalanced by the rules of quantum mechanics, which prevent the electron from simply collapsing into the nucleus. The distance it maintains is absolutely critical. If this fundamental spatial scale were even slightly different, if the electromagnetic force were a bit stronger or the quantum rules a bit weaker, atoms would either collapse or fail to form stable structures altogether. No atoms means no molecules, no chemistry, and certainly no complex life. The distance that defines an atom's structure is the very foundation upon which all complexity is built. This fine-tuning extends far beyond the atomic scale to the very engines of the universe, stars. The process of stellar nucleosynthesis, which forges the heavier elements essential for planets and life, is a spectacularly sensitive dance that depends on a precise hierarchy of distances and energies. Inside a star like our Sun, gravity pulls matter inward, creating immense pressure and heat at the core. This heat provides the protons with enough energy to overcome their mutual electromagnetic repulsion and get close enough for the strong nuclear force to take over, fusing them into helium and releasing the energy that makes stars shine. The range of the strong nuclear force is incredibly short. It only operates over a distance roughly the size of a proton. If this force were even slightly weaker, or its effective distance shorter, protons could never get close enough to fuse. Stars would never ignite. the universe would be a dark, cold sea of hydrogen. Conversely, if the force were stronger, fusion would happen too easily and stars would burn out in a cosmic flash. The existence of long-lived, stable stars, which cook the elements of life over billions of years, hinges on a perfect and seemingly precarious balance between the vast reach of gravity, the specific range of the nuclear force, and the spatial scales that separate particles. Even the largest scales of distance play a crucial role in making the universe habitable. The rate of the universe's expansion, set in the first moments after the Big Bang, had to be exquisitely fine-tuned. If the expansion had been too rapid, matter would have flown apart too quickly for gravity to pull it together into galaxies and stars. The cosmos would be a thin, structureless mist. If the expansion had been too slow, gravity would have quickly pulled everything back together in a catastrophic big crunch long before life could ever evolve. The observed acceleration driven by dark energy adds another layer to this cosmic balancing act. Its value is absurdly small compared to theoretical predictions, yet if it were significantly larger, the universe would have been ripped apart before galaxies could form. The vast distances between galaxies, which we often see as empty and desolate, are actually a prerequisite for a stable, long-lived universe where life has the time and space to emerge. This brings us to a truly mind-expanding possibility, the multiverse. Some cosmologists and physicists, particularly those working with inflationary theory and string theory, suggest that our universe might not be the only one. Instead, it could be one bubble in a vast cosmic foam of universes, each with its own unique set of physical constants and laws. In this vast landscape, the values for the forces, the masses of particles, and the fundamental distances would be different in every universe. The vast majority of these universes would be stillborn or sterile places where atoms never form or stars never shine. But in a rare few, like our own, the numbers would line up just right to allow for galaxies, stars, planets, and eventually observers. In this context, the Anthropic Principle provides a powerful explanation for why our universe appears so finely tuned. We don't live in a special universe designed for life. We live in one of the few possible universes that could contain life. And we are here because its conditions, including its specific spatial scales, allow it. The distance between particles isn't a lucky accident. It's a winning ticket in a cosmic lottery with nearly infinite losing numbers. But if the universe is fundamentally a vast network of information, a cosmic computation where even spacetime is an emergent property, then we are forced to ask a truly staggering question. What is doing the computing? This line of inquiry leads us into the realm of digital physics, a perspective that proposes the cosmos might not just be like a computer, but that it literally is one, a vast, ongoing calculation where the laws of physics are simply the algorithms being run. In this view, the reality we experience is not the primary thing. It is the output, the display, of a deeper, more fundamental informational process happening at the Planck scale. The atoms, forces, and even the space between them are not the foundation but the result. Much like the rich, detailed world of a video game is not made of castles and dragons, but of ones and zeros being processed according to a set of rules. To grasp how something as seemingly abstract as computation could generate our concrete reality, we can look to a beautifully simple model called a cellular automaton. The most famous example is John Conway's Game of Life. Imagine an infinite grid of squares like a gigantic chessboard. Each square or cell can be in one of two states, alive on or dead off. The entire system evolves in discrete ticks of time, following a handful of simple rules that depend only on each cell's immediate neighbors. For example, a live cell with too few neighbors dies of loneliness. a dead cell with exactly 3 neighbors springs to life. From this minimalist setup, something miraculous happens. Out of these simple, local rules, complex global patterns emerge, gliders that drift across the grid, stable structures that act like primitive organisms, even configurations that can function as logic gates and build copies of themselves. The game of life doesn't have any rules for creating distance or motion. Those concepts emerge from the relationships between the cells over time. A glider isn't a thing moving, it's a pattern of ones and zeros being updated, and the illusion of movement across the grid is what we interpret as distance. Now take this idea and scale it up to encompass the entire universe. Proponents of digital physics like Konrad Zuse and later Edward Fredkin suggested that reality might operate on a similar principle. At the very smallest scale, the foundation of everything is a kind of cosmic grid, a cellular automaton operating at the Planck scale. The cells are the fundamental bits of reality, and the universe is the output of this unimaginably vast computation running its program. In this framework, what we perceive as a continuous, flowing reality is actually a series of discrete frames, like the frames of a movie, updating at a rate so incredibly fast that it appears smooth to us. The laws of physics, gravity, electromagnetism, quantum mechanics are not handed down from on high. They are the emergent, high-level consequences of the underlying computational rules. An electron isn't a tiny ball. It's a stable, propagating pattern in this cellular automaton, much like a glider in the game of life. This radically changes what we mean by distance. In a cellular automaton, the distance between 2 patterns is not a pre-existing emptiness. It is simply a measure of how many computational steps or cell updates separate them. 2 patterns that are informationally close might influence each other quickly, while those that are informationally far apart might take many updates to interact. This aligns perfectly with the speed of light being a universal speed limit. It could represent the maximum rate at which information can propagate through the computational grid from one cell to its immediate neighbor. Nothing can travel faster than this single cell per update speed because that's the fundamental clock rate of the computation. Distance becomes a measure of informational separation, or the number of processing steps required for 2 points in the grid to communicate. The vast gulf between stars is not a physical void but a vast number of computational cells that must be updated in sequence for any influence to cross it. This perspective dovetails powerfully with other ideas we've explored. The holographic principle, which says the information in a volume is encoded on its boundary, fits neatly with the concept of a computation that only needs to process surface data to generate a 3-dimensional reality. The quantum foam, with its seething, chaotic fluctuations, could be the visual manifestation of this underlying digital chaos at the Planck scale. And if the universe is a computation, it naturally invites the question of what exists outside of it. Is there a programmer, or is the system self-contained? But perhaps the most profound implication is for the nature of reality itself. If the universe is computational, then it is made of mathematics and logic. The physical stuff we see and touch is a secondary manifestation of a deeper, abstract reality of relationships and information processing. It suggests that the ultimate nature of existence is not material but informational, and that the distances we measure are simply the readable output of a cosmic calculation whose true language is written not in particles or forces, but in bits. But for all our talk of cosmic distances and quantum grains, we must remember that every measurement, every observation of the vast universe is ultimately filtered through the most complex instrument we know, the human mind. Our experience of space is not a direct, unfiltered download of reality. It is a brilliant, ongoing construction project happening inside our heads. Our brains are not passive cameras recording the world. They are active interpreters, constantly taking ambiguous sensory data and weaving it into a coherent, three-dimensional experience. This process is so seamless that we rarely notice it, but it means that the distance we perceive is a carefully crafted interpretation, not an absolute truth. This interpretation can be fooled, as anyone who has seen a mirage on a hot road can attest. The shimmering puddle in the distance isn't water. It's a trick of light refraction that our visual system, desperate to make sense of the information, misinterprets as a nearby object. Virtual reality takes this a step further, hijacking our sensory systems entirely to convince us we are walking through a completely digital space, demonstrating that the feeling of being there and navigating distances can be generated with nothing more than clever code and a headset. These illusions reveal that our perception of space is a best guess, a hypothesis about the world that is usually right but is fundamentally a creation of the mind. This mental construction of space is not a cold, mathematical calculation. It is deeply infused with our emotions and the context of a situation. A growing body of psychological research shows that what we see is influenced by how we feel. Imagine you are wearing a heavy backpack and looking up a hill you need to climb. To you, the hill will literally look steeper, and the distance to the top will appear greater than it would to someone who is rested and unburdened. Your body's state directly alters your visual perception. Similarly, if you are feeling fearful, say, walking down a dark alley at night, the distance to the end of the alley will seem longer than it would on a sunny afternoon. Your mind prioritizing safety makes the threatening environment feel more vast and inescapable. Conversely, if you are reaching for a tool you use all the time, your brain perceives it as closer than an unfamiliar object placed at the exact same distance. These aren't just interesting quirks, they are evidence that our perception of space is a functional interface designed for action. The brain isn't trying to show us the world as it is in some objective sense. It's trying to show us the world as we need to see it to navigate our goals, our resources, and our fears effectively. Distance becomes a subjective experience, tailored in real time to our inner state. This profound subjectivity forces us to confront a deep philosophical question that has echoed from the studies of psychologists all the way back to the debates of philosophers like Immanuel Kant. If our perception of distance is so malleable, so dependent on our psychology and physiology, can we ever say that it has a truly objective basis? Is the meter between your hand and your coffee cup a real property of the universe? Or is it just a useful story our brain tells us to help us grab the cup without spilling? Science, of course, operates on the assumption that there is an objective reality out there, and that our measurements, despite being processed through our minds, can converge on a shared, consistent truth. We can all agree that the coffee cup is about 30 centimeters away because we can all use the same ruler and get the same result. This intersubjective agreement is the bedrock of physics and engineering. Yet, the psychological evidence suggests that our raw, unfiltered experience of that 30 centimeters is not fixed. It is a dynamic interpretation. This doesn't mean that space is an illusion, but rather that the feeling of distance, the immediate, visceral sense of near and far, is a property of consciousness itself. This blends the hard science of measurement with the soft science of phenomenology, the study of lived experience. It suggests a universe with two complementary layers, an objective, physical reality of spacetime that can be described by mathematics, and a subjective, psychological reality of spatial experience that is unique to each conscious observer. The distance between galaxies is an objective fact, but the awe we feel when contemplating that distance is a mental construct. One can exist without the other, but for us, they are forever intertwined, revealing that to fully understand distance, we must explore not only the outer cosmos but also the inner universe of the human mind. The hunt for the fundamental nature of spacetime is accelerating, moving from the blackboards of theorists into the precise domain of experimental physics. For decades, the idea that distance itself might be the builder of reality was a beautiful but untestable hypothesis. Today, that is changing. A new generation of instruments and techniques is being designed to probe the very fabric of the cosmos, searching for the subtle fingerprints of a granular or emergent spacetime. These aren't just incremental improvements. They are leaps into the unknown, offering the first real chance to witness the pixels of reality. One of the most promising frontiers is the detection of gravitational waves. When LIGO first heard the chirp of two black holes colliding over 1 billion light-years away, it opened an entirely new window on the universe. But future observatories like the planned Laser Interferometer Space Antenna, or LISA, will listen for waves with much longer wavelengths generated by the mergers of supermassive black holes. These waves have been traveling across the universe for eons, and their journey may have taken them through the quantum foam at the smallest scales. If spacetime is grainy, it could impart a subtle, random noise onto these waves, a kind of static in the signal. By analyzing the pristine signals collected by space-based detectors, physicists hope to find this telltale whisper of a foamy spacetime, a faint hiss of underlying structure betraying the smooth classical continuum. Alongside these cosmic listeners, scientists are building universe simulators right here on Earth. Using incredibly controlled systems like arrays of supercooled atoms or ions suspended in electromagnetic traps, researchers can create quantum simulators. These aren't digital computers running a simulation in code. They are analog systems where the quantum components themselves behave according to the same mathematical rules that might govern spacetime. By carefully tuning the interactions between these atoms, physicists can essentially trick them into behaving like a miniature, lower-dimensional universe. Watching how entanglement spreads through this system, how correlations between the atoms evolve, could provide a stunningly clear model for how geometric properties like distance and curvature might spontaneously emerge from a network of quantum connections. It's like watching a crystal form in fast forward, giving us a tangible, observable example of how order and structure can arise from chaos. Perhaps the most audacious goal is to create a lab-based analog of a black hole or another extreme spacetime geometry. While we can't create a real singularity, we can use clever materials to mimic its effects. Certain configurations of ultra-cold atoms, known as Bose-Einstein condensates, or even flowing water, can be engineered so that sound waves traveling through them behave exactly like light waves trying to escape a black hole event horizon. This creates an effective dumb hole or sonic black hole. By studying how sound and information behave at this artificial horizon, we can test ideas about Hawking radiation and information loss in a controlled setting. These experiments allow us to bring the most extreme consequences of general relativity and quantum mechanics into the laboratory, offering indirect but powerful insights into how spacetime behaves under conditions we could never otherwise study. The ultimate dream, of course, is to somehow probe the Planck scale directly. This seems impossible with traditional particle colliders. Building one powerful enough to reach those energies would need to be larger than our solar system. But some theorists propose a backdoor. If spacetime is indeed discrete, it might violate a fundamental symmetry known as Lorentz invariance in very subtle ways. This means that the speed of light might not be perfectly constant for all wavelengths. ultra-high-energy cosmic rays, which are particles from deep space carrying millions of times more energy than anything we can produce at the LHC, could be our messengers. By studying these rare and powerful particles with observatories like the Pierre Auger Observatory, we might detect tiny deviations in their behavior that reveal the granular texture of spacetime they've traveled through. It's a long shot, but it represents the kind of creative, bold thinking that is now driving the field forward. All of these endeavors, from listening to the whispers of black holes to building miniature universes in a lab, are converging on a single, monumental question. They are not just testing specific theories like string theory or loop quantum gravity. They are testing a foundational paradigm. Is the smooth, continuous spacetime of Einstein's relativity the final word? Or is it a magnificent emergent illusion, a collective behavior that arises from something deeper and more fundamental? The answer will determine the next century of physics. If these experiments find what they are looking for, it will trigger a revolution as profound as those sparked by quantum mechanics and relativity. We will have to rewrite our textbooks not just on particles and forces, but on the very nature of reality itself, finally understanding that the vast, empty distances between the stars are not nothing, but the source of everything. This profound shift in perspective, from seeing the universe as a collection of isolated objects to understanding it as a vast network of relationships, doesn't just change our physics, it changes us. It challenges the very core of how we see ourselves and our place in the cosmos. For centuries, the dominant narrative, reinforced by both science and daily experience, has been one of separation. We are individuals distinct from each other and from the natural world, moving through an empty void. But if the emerging picture from physics is correct, this sense of separation is the ultimate illusion. The space between us is not a barren gap to be crossed. It is the very substance of our connection, the active medium through which we are fundamentally intertwined. This isn't just a poetic sentiment. It is a potential conclusion drawn from the mathematics of entanglement and emergent spacetime, suggesting that our deepest reality is one of unity, not division. This radical rethinking of distance could fundamentally reshape our relationship with the natural world. Our current ecological crises often stem from a worldview that sees humanity as separate from and superior to the environment. We view forests, oceans, and atmospheres as resources to be extracted or voids to be filled with our waste, existing at a safe distance from our lives. But if we truly internalize the idea that the space between things is a connective, generative tissue, that perspective shatters. The atmosphere isn't just around us. The process of our breathing is a continuous, intimate exchange with it. The river downstream isn't just far away. Its health is directly linked to the choices made upstream, connected by the water's path and the life it carries. An ecological ethic born from this understanding wouldn't be about managing separate resources, but about nurturing the health of the entire relational network. It fosters a sense of inherent responsibility, not out of fear or obligation, but from the recognition that to harm any part of the system is to ultimately harm the whole, because we are not in the system, we are the system expressed in a particular form. On a human level, this concept of distance as connection offers a powerful antidote to the modern epidemic of loneliness and isolation. In a world where digital screens can make us feel more connected than ever yet more profoundly alone, the physics of entanglement provides a startlingly beautiful counter-narrative. The feeling of missing a loved one on the other side of the planet is not just a psychological state. It could be seen as a dim, human-scale awareness of a deeper quantum connection that physics suggests is real. While we can't send messages faster than light, The theory implies that the particles that once were close, that were part of the same system, retain a ghostly correlation. This doesn't mean we can psychically communicate, but it does mean that the vast physical separation we experience is, at the most fundamental level, a kind of surface phenomenon. The apparent chasm between you and another person is not the final word on your relationship. This scientific insight can reframe our emotional experience of distance, transforming it from an absolute barrier into a temporary condition of our current perspective, offering a profound sense of comfort that at the deepest level, no one is ever truly alone. Existentially, this view can alleviate the terrifying weight of absolute separation that has haunted philosophy for centuries. The anxiety of being a lone consciousness trapped inside a skull, peering out at an alien and distant world, is a direct product of the old materialist paradigm. If spacetime and matter are emergent properties of a deeper informational or relational reality, then the boundary of our skin is no more a fundamental barrier than the event horizon of a black hole is a solid wall. It is a transition zone, a region of complex interaction. Your mind is not locked inside your brain. It is a process that is inextricably entangled with its environment through a constant flow of light, sound, energy, and information. You are not a marble statue of a self placed in a room called the universe. You are more like a whirlpool in a river, a stable, recognizable pattern, but utterly dependent on and inseparable from the continuous flow of water that constitutes you. This shifts the foundation of identity from isolation to participation, suggesting that we are verbs, not nouns, dynamic events within the cosmic network, rather than static objects placed within it. Ultimately, these ethical and existential reflections show that our scientific quest to understand the universe is never a sterile, detached exercise. The models we build don't just describe reality out there, they shape the reality in here, inside our minds and our societies. A physics of separation has, perhaps unconsciously, supported ideologies of individualism, competition, and environmental disconnection. A physics of fundamental relationship, built on the primacy of connection across distance, offers a new foundation for how we might live together. It provides a scientific basis for empathy, for compassion, and for a holistic worldview that has long been advocated by wisdom traditions across the globe. It suggests that the greatest mysteries of the cosmos are not only about the birth of stars or the nature of black holes, but are also intimately concerned with the nature of connection itself, revealing that the space between hearts and the space between galaxies might be different expressions of the same beautiful underlying truth. Long before telescopes or particle accelerators, humanity was already gazing into the heavens and the depths of existence, using the language of myth and story to articulate a profound intuition about the nature of reality. Across vast continents and isolated cultures, a remarkably consistent theme emerges from these ancient cosmologies. The universe did not begin with a solid thing, but with an empty space, a fertile void that held the potential for all creation. This primordial nothingness was not seen as a mere absence. It was recognized as an active, creative force, the necessary stage that must exist before any actors can appear. These stories reveal a deep, pre-scientific understanding that what we call distance might be the most fundamental ingredient of all. Consider the Norse conception of Ginnungagap, the great and yawning void that existed before the world. In this tradition, there was neither sand, nor sea, nor cool waves. There was only this immense gap, flanked on one side by a realm of fiery heat and on the other by a land of bitter cold. Where these two forces met in the middle of Ginnungagap, a reaction was sparked, and from that interaction in the void, the first giant, Ymir, was formed. The story makes it clear that the gap itself is primary. It is the container, the context, without which the contrasting elements could not interact and generate life. Unpack is not passive emptiness. It is the enabling condition for all that follows, the spatial prerequisite for creation. On the other side of the world, the Aboriginal cultures of Australia describe the dream time or dreaming, a concept that is often misunderstood. It is not a time long past in a chronological sense, but rather a sacred, eternal dimension that underpins reality. In the dreaming, ancestral spirits emerged from a formless, featureless plane and began to journey across the land. As they moved, they sang the world into existence, naming the animals, carving the riverbeds, and forming the mountains through their epic travels and rituals. The landscape itself is literally sung into being through the movement and actions of these beings across the vast, empty distances. Here, space is not a backdrop. It is the canvas upon which the song of creation is written. The distances traveled are not incidental. They are integral to the act of creation itself, with each location embodying the events that happened there. The world is a tapestry of spatial relationships whose meaning is derived from the journeys that formed them. This pattern repeats itself across the globe. In ancient Egyptian mythology, the god Atum emerges from the primordial waters of Nun, a dark, infinite, and chaotic ocean of potentiality that exists before differentiation. The Enuma Elish, the Babylonian creation epic, begins with the mingling of the fresh waters Apsu and the salt waters Tiamat, a union that occurs within an undefined spatial void. Even the concept of the Tao in Chinese philosophy, often translated as the Way, implies a fundamental order or path that is inseparable from the spatial and relational structure of the universe. These narratives, born from cultures that had no contact with one another, all point toward the same profound insight. That form emerges from the formless, and that matter is preceded by the spatial relationships that make its organization possible. This cross-cultural resonance is staggering. It suggests that the intuition of space as a foundational reality is not a modern invention of theoretical physics, but a deep-seated archetype within human consciousness. For millennia, we have sensed that the vast separations between things are not merely gaps to be crossed, but are the very ground of being from which things themselves arise. The ancient mythmakers, using the language of symbol and story, were grappling with the same fundamental mystery that today's physicists are tackling with mathematics and particle detectors. What is the true nature of the void, and why is there something rather than nothing? This rich tapestry of ancient thought does more than just provide a historical curiosity. It enriches and deepens the modern scientific quest. It reminds us that our drive to understand the cosmos is not a cold, purely rational exercise, but a continuation of a timeless human conversation. When a physicist like John Wheeler describes the quantum foam or proposes the participatory Anthropic principle, they are walking a path that was first trod by shamans, poets, and storytellers. The language has changed from gods and spirits to metrics and tensors, but the underlying fascination with the creative power of emptiness remains utterly unchanged. This connection invites a wonderful humility into our search for knowledge. It suggests that our most advanced theories are not appearing in a vacuum, but are instead the latest expressions of an enduring human endeavor to comprehend our place in the cosmos. The fact that a 21st century physicist working with holographic principles and a Norse skald recounting the tale of Unpack are both pointing toward the primacy of space tells us that this idea is not just technically compelling, but is also deeply meaningful to the human spirit. It bridges the alleged gap between the scientific and the mythical, revealing them as two different languages describing the same breathtaking reality. This timeless intuition, woven into the very fabric of human thought across ages and civilizations, lends a powerful weight to the radical idea that we are now beginning to mathematically formalize, that everything we see and know might indeed be built from nothing but relationship, connection, and distance. We have journeyed through mathematics and myth, through the quantum foam and the cosmic expansion, all pointing toward a reality where distance might be the fundamental substance of everything. But as we reach for this ultimate understanding, we confront a formidable and deeply human barrier: the limits of our own language. The words we have, the metaphors we rely on, were forged in a world of medium-sized objects moving at slow speeds. They are spectacularly ill-equipped to describe the bizarre, non-intuitive nature of reality at its most fundamental level. Every term we use is, in the end, a placeholder, a clumsy approximation for a concept that might truly be ineffable, beyond our capacity to articulate. Consider the very metaphors we've leaned on throughout this exploration. We speak of the fabric of spacetime, evoking the image of a cosmic bedsheet that can be stretched and warped. This is a powerful and intuitive image, but it is also a lie. A fabric is made of woven threads. It has a texture and a substance. Spacetime, if it is emergent or quantized, is not like a fabric. It may be the fabric, but in a way that is utterly alien to any cloth we have ever touched. We talk about a cosmic network or a web of entanglement, importing terms from computing and spiderwebs to describe the connectedness of the universe. These metaphors are useful because they give our minds something to hold onto, a familiar hook for an unfamiliar idea, but they are also dangerously limiting. They inevitably import properties from their original context that do not apply to the new one, subtly steering our thinking down familiar paths when we need to be blazing entirely new trails. Even the precise scientific terminology we employ is often just a label for our ignorance, a fancy name for a phenomenon we don't truly comprehend. We say spacetime emerges from a more fundamental network. The word emergence suggests something coming into view, like a whale surfacing from the depths, but this implies the thing was already there, just hidden. Is that what's happening, or is it a genuine creation of something entirely new, a phase transition where the very concept of where and when crystallizes out of a pre-geometric chaos? Similarly, we say space is quantized, meaning it comes in discrete, indivisible chunks. This borrows from the idea of counting whole numbers, but it doesn't begin to convey what the actual experience of a pixelated universe would be like. These words are the best we have, but they are the map, not the territory. They are the recipe, not the meal. They allow us to do the math and make predictions, but they often fail to provide a genuine aha moment of understanding in the way that intuitively grasping a metaphor can. This profound linguistic challenge is not a sign of failure. It is a signature of the frontier. It is what happens when human consciousness, which evolved to avoid predators and find ripe fruit, bumps up against the absolute weirdness of the cosmos. Our language is a tool for sharing experience, and we simply have no common experience of what it's like to be a quantum fluctuation or a vibrating string in a 10-dimensional Calabi-Yau manifold. We are like a race of beings who have lived their entire lives in a flat, two-dimensional plane, suddenly trying to describe a sphere to one another. All of our vocabulary is based on flatness points, lines, angles. The concept of curvature would be unimaginable, a paradox. We might invent clumsy phrases like a line that bends away from itself or a shape that is finite but has no boundary, but these would be descriptions, not true understanding. The only way to truly get it would be to somehow step outside the plane and see the sphere for yourself. This is the position we find ourselves in with modern physics. The mathematics provides a formal description that is incredibly accurate and powerful, but translating that formalism into plain language forces us to use analogies that are always incomplete and sometimes misleading. This forces a necessary humility. It reminds us that our understanding of the universe is always partial, always provisional. The maps we draw are incredibly useful, but we must never confuse them with the reality they are attempting to represent. The inability to perfectly articulate these ideas is not a wall, it is an invitation. It encourages an openness to new ways of thinking, to entirely new paradigms that might one day provide a language more suited to the task. It asks us to hold our most cherished theories lightly, to be ready for a future discovery that will make our current best metaphors look as quaint as Aristotle's crystalline spheres. The struggle with language is the growing pain of a species expanding its mind, reaching beyond the world of its senses to touch the true, and perhaps ultimately silent, architecture of reality. Let's try a little thought experiment together. Close your eyes for a moment and picture yourself shrinking, not just getting a little smaller, but shrinking down past the size of an atom, past the size of a proton, down to the very smallest scale possible, the Planck length. At this scale, the universe wouldn't look like anything you've ever seen. There's no left or right, no up or down, no clear here or there. Instead, you'd find yourself in a seething, turbulent ocean of energy, where space-time itself churns and froths like a bubbling pot of water. Tiny wormholes blink in and out of existence, connecting points that might be light years apart in our everyday reality. In this realm, the very idea of distance becomes fuzzy and uncertain, because at the Planck scale, the smooth, continuous space we're used to dissolves into a dynamic, chaotic foam. This isn't just science fiction, it's what physicists like John Wheeler meant when they described the quantum nature of reality, where distance isn't a fixed measurement but a fluctuating, probabilistic concept. Now let's stretch our imagination in the opposite direction. Think about quantum entanglement, that spooky action at a distance that even Einstein found puzzling. Imagine you and a friend each hold one of a pair of entangled particles. You could travel to opposite sides of the galaxy, and the moment you measure your particle, you instantly know the state of your friend's particle, no matter how far apart you are. There's no signal traveling through space. The connection seems to transcend distance entirely. It's as if the universe is operating like a vast, decentralized mesh network, the kind used in some wireless systems where every device communicates directly with its neighbors without relying on a central hub. In such a network, the physical distance between devices matters less than the strength and pattern of their connections. Similarly, in an entangled universe, what appears to us as vast spatial separation might be nothing more than a surface-level illusion, with everything fundamentally interconnected at a deeper, informational level. This isn't just an abstract idea. It's a key insight from theories like the Holographic Principle, which suggests that the three-dimensional world we experience could be a projection from a two-dimensional surface where distance is encoded as relationships between bits of information. Bringing this back to our everyday lives, consider how you experience distance emotionally and psychologically. When you're far from someone you love, that distance can feel immense, almost tangible, a heavy weight of separation. Yet, when you see their face on a video call or receive a message from them, that distance seems to collapse, bridged by technology and emotion. In those moments, you're intuitively tapping into a truth that physics is only beginning to grasp. Distance is not just a physical quantity, but a relational one. It's shaped by context, connection, and perception. The warmth of a close conversation can make 1,000 miles feel like nothing, while the cold silence in a room with someone you're disconnected from can make a few feet feel like an uncrossable chasm. This daily experience mirrors the cosmological idea that distance might be emergent, not a fundamental feature of the universe, but something that arises from more basic relationships, whether they're quantum entanglements or human emotions. To make this even more concrete, let's use a simple analogy. Think of a spider's web glistening with morning dew. From a distance, it looks like a single, delicate structure, but up close, you see it's made of countless individual strands connected to one another. The web's strength and flexibility don't come from any one strand, but from the way all the strands work together. Now, imagine that the universe is like that web. The points where the strands connect represent fundamental units of spacetime, and the distances between them are defined by the relationships and tensions within the web. What we perceive as empty space is actually full of these invisible connections, humming with activity and meaning. This is the essence of emergent spacetime, a reality where distance isn't an empty void but a rich tapestry of relationships waiting to be explored and understood. By engaging with these ideas personally, we transform abstract physics into something visceral and relatable. We begin to see that the mystery of distance isn't confined to textbooks or laboratories. It's woven into the very fabric of our lives, from the way we connect with each other to the way we experience the world around us. This bridge between the cosmic and the personal makes the science not just accessible but deeply compelling, inviting us all to become active participants in the grand adventure of understanding reality. We have traveled an extraordinary path, from the paradoxes of Zeno in ancient Greece to the quantum foam dancing at the Planck scale, from the absolute stage of Newton to the warped fabric of Einstein, and from the holographic principle to the emergent spacetime born from entanglement. This journey has challenged the most fundamental aspect of our reality, the very substance of existence itself. We began by asking if everything we see and touch could be built from nothing but distance, and the evidence we've uncovered points toward a breathtaking and radical yes. This isn't a minor adjustment to our worldview, it is a complete inversion of it. We are asked to let go of the comfortable idea that solid matter is the primary stuff of the universe, and to embrace a far more mysterious and beautiful possibility, that the true foundation of all things is the relationships between them, the spatial connections we have always mistaken for empty nothingness. This perspective transforms the cosmos from a collection of isolated objects into a single, dynamic, and deeply interconnected network. The vast distances between galaxies, the gap between your hand and the screen, even the space within an atom, these are not voids to be crossed but the active, generative medium of reality itself. What we perceive as separation is actually the substance of connection. The universe is not in space. Space is the universe, constantly evolving, stretching, and weaving the tapestry of existence through the fundamental language of distance. This realization invites a profound sense of wonder, urging us to see the world not as a place filled with things, but as a magnificent dance of relationships, where every star, every planet, and every conscious being is a unique expression of the spatial geometry that binds it all together. As we stand at this frontier of understanding, it is clear that the mystery is far from solved. The theories we've explored are still in their infancy, and the experimental evidence we so desperately seek remains just out of reach. But that is the very essence of science, the courageous pursuit of answers to questions that stretch the limits of our imagination. The greatest discoveries always begin with a willingness to question our most basic assumptions, to look at the familiar and see the strange and wonderful truth hidden within. The idea that distance builds everything is one of those magnificent questions that will drive scientific inquiry for generations to come, pushing our technology and our minds to new heights as we strive to uncover the ultimate architecture of reality. So the next time you gaze up at the night sky, let your perception shift. Don't just look at the points of light, contemplate the immense dark spaces between them. See that darkness not as an empty void, but as a field of infinite potential, the fundamental canvas upon which the story of the universe is written. Remember that the light from those distant stars has traveled across billions of years, its journey made possible by the stretching and evolving of that spatial canvas. The distances are not barriers keeping us apart, they are the very threads that connect us all into a single cosmic whole. Thank you for embarking on this incredible journey through the mysteries of space and existence. If these ideas have sparked your curiosity, share your own thoughts and questions in the comments below, and be sure to subscribe to join us as we continue to explore the deepest wonders of the universe.